one-of-a-kind intricate bronze sculptures that fascinates metallurgists worldwide even today. Exquisite and highly detailed, the finest lost wax sculptures take several weeks or months to make. The process starts with the creation of a detailed wax model. A clay mold is then created with the wax model. The mold, when heated, loses the wax while retaining the clay mold. Molten bronze is then poured into the clay molds, which are then broken after cooling to reveal the bronze statue. This makes each and every bronze work unique and one of a kind. The beauty of the bronze statue lies in the details. This technique was brought into a level of excellence during the Chora dynasty, which ruled in South India during the period from 850 to 1250 CE. It may be noted that even today, Chora bronzes continue to be made in the same fashion and are highly sought after across the globe.
So good morning everyone. Actually, Director of IT Madras bit delayed. So he'll be joining us at 9:20. But anyhow, we are going to start the program. So Namaste, Vanakkam and good morning to one and all present here. And also the viewers around the world connected online. A warm welcome to much awaited Indo-German workshop titled Recent Advances in Precursor Derived Ceramics Innovations and Translational Research PDC 2023, organized by the Department of Metallurgical and Materials Engineering, IT Madras, University of Bayreuth. It is sponsored by the Indo-German Science and Technology Center and co-sponsored by Carbonundum Universal Limited and Nesch and Brucker. The workshop will be followed by a one-day international conference on advanced ceramic technologies for futuristic mobility under the Institute of Eminence initiative that was launched by Government of India. I cordially invite our distinguished guest, Shri R. Madan, Director of Indo-German Science and Technology Center, Shri Anant Seshan, Managing Director of Carbonundum Universal Limited, to please come onto the dais. I also invite Professor Ravi Kumar, Head of the Department Metallurgical and Materials Engineering, IIT Madras, and Professor Gunther Motz, Ceramic Materials Engineering, University of Bayreuth, Germany, to come onto the stage. I now request everyone to stand for the Tamil Thaivarthu and followed by Vande Mataram.
அதில் சிறந்த திராவிடனல் திருநாடும் தக்க சிறு பிறை முதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழனங்கே தமிழனங்கே சீரிழமை திறம்பியந்து செய்ய மறந்து வாழ்த்துதுமே வாழ்த்துதுமே வாழ்த்துதுமே
वन्दे मातरम् शुभ्रज्योत्स्ना पुलकितयामिनी पुल्लकुसुमित द्रुमदलशोभिनी सुहासिनी सुमधुरभाषिणी सुखदां वरदां मातरम् वन्दे मातरम् वन्दे मातरम्.
Everyone, please be seated. I request the workshop coordinator, Dr. Ravi Kumar and Dr. Gunther Morse, to make the opening remarks.
Good morning. Professor Kamakoti will be delayed by a few minutes, so he'll join us very soon. Shri Madan, Director of Indo-German Science and Technology Center. Shri Ananta Seshan, Managing Director of Carborundum Universal Private Limited. Dr. Gunther Morse from the University of Bayreuth. Colleagues from India and abroad, mostly from Germany. Namaste, Vanakkam, good morning and Guten Morgen. I would like to extend a warm welcome to you to this beautiful campus of IIT Madras. Herzlich willkommen auf diesem wunderschönen Campus des Indische Institute für Technologie Madras. The workshop was conceptualized in the mid of last year when I was visiting University of Bayreuth, and we are happy that we are able to organize this event in IIT Madras in less than 7-8 months. And thanks to Igstc for supporting this and making this happen. The focus of the workshop is twofold. We would like to identify the translational potential of precursor-derived ceramics and also bring young researchers under one roof to brainstorm on how to take it forward. The ceramic engineering at University of Bayreuth has strong translational research component, which I have seen myself, and a very strong industry connect in the area of PDCs. And hence, we could not have found a better partner other than Gunther Morse to organize this workshop jointly. We have nearly 40 plus speakers during the next 3 days with a tightly packed schedule. I hope you will have a productive scientific interaction during the next 3 days. Over to Gunther Morse.
Dear ladies and gentlemen, namaste. First of all, I would like to extend a warm welcome to all participants of the PDC workshop. I'm very happy that so many friends, colleagues, and interested scientists from all over the world were able to come. In particular, I thank Professor Kumar and his team for the preparation of the application, the excellent organization of the workshop, and the kind hospitality. I would also like to thank the Igstc in particular, but also the sponsors for the financial support, because they would not be able to hold the workshop without money. But I would also like to thank the IIT Madras for the hospitality and that we can use this beautiful campus for our event. The IIT Madras is a very special place with a long Indian-German history. It was founded in 1959 with the help of the West German government, and the agreements for this were made in 1956 at a meeting between the Indian President Nehru and the German Chancellor Adenauer. IIT Madras was started with technical, academic, and financial assistance from the government of West Germany and was at the time the largest international educational project sponsored by the West German government. You can find the signs of this history in the street names like Bonn and Delhi Avenue. It is therefore important to us to continue this tradition with the workshop. In this respect, we were faster than our Chancellor Olaf Scholz, who visited India only 2 weeks ago to intensify the collaborations between India and Germany. By the way, we already started our talks to intensify the cooperation in June last year during a birthday party in Bayreuth, and Professor Kumar also attended. The IIT campus is not only a perfect place to get to know each other and exchange scientific ideas, but especially in today's turbulent times, it is an example of the peaceful coexistence of different cultures, countries, and nationalities. This promotes intercultural exchange, tolerance, and understanding. This extraordinary and unique campus is also an example of how people and wild animals live together peacefully and nature is protected. So I hope that this workshop will not only be very interesting from a scientific point of view, but it will also be a good opportunity to get to know each other and to promote international exchange and as well as understanding. Therefore, I wish all participants an interesting workshop, and that everyone can enjoy also the cultural program. And at last but not least, I would congratulate all ladies present in the room, because today is the International Women's Day. And at the end, I would like to thank you for attention. I wish you a very excellent, nice, and good workshop. Thank you.
I now request our guest of honor, Shri Ananta Seshan, Managing Director of Carbondum Universal Limited, to say a few words about the workshop.
Good morning, ladies and gentlemen. First of all, a big thank you to Professor Ravi Kumar for this invitation and honor to be here with you today. It's a pleasure, sir, Mr. Madan and Professor Kamakodi and Dr. Gunther Motz, and all of you. I come from a company, Carbondum Universal, and I have the pleasure and honor of leading that company. We started off as an abrasives company long ago in 1954, starting off with two classes of materials, oxides and carbides, and leveraging one of the properties, which is hardness, and then created a business into abrasives. And that's been our philosophy all along, working on just two classes of materials and then discovering possibilities by leveraging the properties of these materials. Moving on from hardness to thermal resistance to refractoriness to electrical conductivity to the dielectric strength, and then putting together forms through processes, starting off with a humble coating process or a molding process and moving on to 3D ceramics today. And today, this workshop gives us one more new process, a forming process called precursor-derived ceramics, which holds immense possibilities. And that's what excites us as a company. And that's what excites me as a student of material science. So it's a double pleasure for me, one, to represent the company, which is now a global company, focusing on from being an abrasives to a material science company, and then moving on further. And two, as a student of material science, to see what the new things are and getting excited about it and learning about it every day, and discovering possibilities of setting new trends and new possibilities for the future. So looking at the kind of program Professor Ravi Kumar has put in, morning, sir. And the kind of distinguished speakers we have and the exciting subjects, I just wish I could be here for the rest of the 4 days. So my colleagues are going to be there, and to all of you, wish you a very enjoyable 4 days, lots of learning, and exciting times ahead. Thank you so very much.
Now I request Professor Kamakodi, Director of IIT Madras, to deliver the presidential address.
A very, very good morning and welcome to IIT Madras campus. There are subjects where I have a reasonable knowledge, but this subject I am completely zero. But still, whatever little knowledge I derived from Professor Ravi Kumar yesterday, what I understand here is that there is a need for us to develop materials that are of lesser weight, but at the same time has more strength. And ceramics actually gives you certain, very nice combinations of materials which can basically withstand our, which has very good thermal and probably electrical properties, and at the same time will have a reduced weight. This is what I get from this. Am I correct? right? Okay, thanks. So, friends, IIT Madras as an institute has been for last at least 2 decades, have been focusing on interdisciplinary research. In this context, we have started multiple interdisciplinary efforts, specifically in the area of aerospace engineering, energy consortium, and sustainability. We also are having multiple startups that are looking at agriculture. So these are some of the 4 important areas that we are touching. And in each of these areas, for example, we have a project in which we are developing drones. We have a project where we are 3D printing rocket engines. We have a project in which we are developing an e-plane, which will be an e-taxi. All these, as we see, require materials, interesting materials, new combinations of materials that will have good strength, at the same time will withstand certain adverse hostile temperature and other environmental conditions. We have successfully tested many materials, and I think some of them have really given very good results. So when we look at this particular topic, all these initiatives that we have taken, for example, we also have a project on Hyperloop, where we are trying to develop pods that will go at super speed inside a vacuum tube. And then what will be the property of the material that will make this Hyperloop? And it works on levitation, so the weight has to be less. The speed is quite high. The type of turbulence that may happen, we don't know. And these are all very interesting research work that we have taken. And I'm sure this collaboration between the German universities, the industry, and also DRDO and other agencies, both strategic and civilian agencies, I'm sure it is going to be very exciting. We are also having many interdisciplinary dual degree courses, wherein we are looking at people with any degree to develop a passion over 2 years after they join the undergraduate course to pursue an entirely new discipline. We are now introduced around 14 dual degree courses, and I'm sure we will have many courses specifically in metallurgy and material sciences, specifically looking at some of the interesting aspects of new materials, including ceramics. I really feel, I'm very confident that this particular effort will bring in more young students interested in the field of metallurgy and material science. Last one, I am also very confident that there's quite a bit of entrepreneurial efforts that can be taken, and many of them can become successful if you have a very good collaboration. There is a lot of scope for translational research here, that we have many end products. At the same time, we have many requirements, and there are many research work that is happening. I think there will be a common spot where we will find all these research that you do, all the new materials that you develop, all the new techniques you develop, will ultimately find an end use in an industry, and hence these research can be extremely translational. So with all these great hopes, I again invite all of you to this wonderful workshop, and I'm sure that these couple of days will be very, very fruitful, and I look forward to many more technical collaboration between IIT Madras and the universities, industry, and the agencies. Thank you very much.
I request Professor Kamakoti V, Director IIT Madras, to present a memento to R. Madan, Director of IGSTC. Now I request Professor Gunther Modes to present a memento to Sri Anantha Session. Now I request Professor Ravi Kumar to present a memento to Professor Kamakoti, Director of IIT Madras. Now I request Sri R. Madan to launch the workshop with the opening of the abstract books. Yes. Yes. Thank you, sirs. I request Professor Gunther Modes to take over this session.
Yeah, good morning again to everybody. And it's a pleasure for me to be the chair of the first session. And I would like to introduce you Mr. Madan from the Indian German Science and Technology Center. And he introduces the IGSTC and gives the first presentation. Thank you so much.
Just a second, see presentation loading.
Very good morning to all of you. Nice to see many known faces again. So let me just take you through what IGSTC offers straight away. So a little about IGSTC. think you have to do enable, yeah. Now you see? Yeah, now it's is it not happening? Well, as they are doing this, yeah, I just should tell you that IGSTC, yeah, it's a joint initiative of the German Ministry for Education and Research and the Indian Ministry of Science and Technology, mainly the Department of Science and Technology. So we get 4 million euros from each government every year for funding projects in science and technology, for networking, and for also supporting early career researchers and women scientists. So let me quickly take you through what IGSTC does. So if you look at the vision, mission, and mandate, I would say 4 main areas. One is look at applied research projects. Second is networking. Third is public-private partnership. And the fourth is connecting early career researchers and networking the young minds. So this is basically the mandate, vision, mission put together. So let me just give you a brief about the S&T landscape between India and Germany. I think there is so much of similarity between India and German in the S&T landscape. So if you look at both our countries, of course I will talk about BMBF and DST as the main funding agencies. We also have other funding agencies in both the countries, and I think like the DFG and DLR, the aerospace, India has similar setup in India. And then you have an entire rank of research institutions in both the countries, which are very similar with different agendas, but very similar row of activities. We then follow that with educational institutes. Again, very similar. You have the technical universities, applied science universities, you have excellence initiative universities in Germany, and similarly you have the ICERs, IISc, IITs, and NITs in India. And then you have a lot of state-run universities and research institutes, both in Germany and India. And of course, they're all trying to connect with industries. And I think what happens usually is you try to connect 1:1, but what IGSTC has through its programs, it helps you to connect to any level. So that's the advantage of using the IGSTC program. So you can actually connect multiple levels through IGSTC. So I will go through my programs, and then you will realize that this is possible. So our feather in the cap program, I will call it, is the 2+2 projects. So because this is where most of our money is put in. The 2+2 projects basically are one German industry, one German research or academic partner, along with one Indian industry and one Indian academic or research partner. 4 of them come together and apply for a project. So these are projects in different thematic areas which we announce. And the German side gets 450,000 euros for the project. The Indian side gets 3.5 crores. So the tenure of these projects are 3 years. We select 7 projects every year. And we expect the project to have a TRL level of close to 3 before you start the project. And what we do is, after 3 years, out of the 7 projects, we take 2 successful projects, the top 2 successful projects, and we fund them further for another 2 years. And here again, the German side gets euro 300,000 and Indian side gets 2.3 crores. So if you see, the overall budget for one program could be close to 14 to 15 crores for this project, if you're coming for the phase 1 and phase 2. And we have thematic areas every year. So the next call will be on waste to wealth and sustainable packaging. So that's going to be the next call. And it's waste to wealth on any areas. We'll be coming up with specific areas by the end of this year. So I think that's an area where you could also think about workshops in the near future so that you can connect with the German institutions and industry. So we funded 50 projects, and these are some of the areas we did in the last few years. We are a young center. We are just 12 to 13 years old. And we have 23 ongoing projects, out of which 4 of them are belonging to IIT Madras. These partners are from IIT Madras. So some of the examples of the projects. So what we expect at the end of these projects are technologies. So we could have technologies. These are some of them which have come up from the project. We could have startups, spin-off startups, which we'll fund further. And we could have pilot plants. These are some of the pilot plants which are a result of the 2+2 projects. So this is something what we expect at the end of the project. The other program we fund is the reason you're here. It's bilateral workshops. And we fund this for networking. You know very well. I think we're so happy to see so many people here from Germany and from India, in fact. So the idea is to network on a very focused and specific topic. And the participation is from 30 to 40 per workshop. And we fund the entire workshop close to 30,000 euros if it is in Germany, and 25 lakhs or a little more if it is in India. It covers the transportation, the international travel costs, the domestic stay, and most of the logistics. So this is again up to 12 workshops a year are funded by Igstc. Again, this goes through a scientific committee, and there are, I would say the success rate is close to 40%, 30 to 40%. In the 2+2, the success rate would be 25 to 20%, around that. This is an interesting program we started recently. It's called the Igstc Industrial Fellowship. This is basically to expose researchers in India to German industrial ecosystem. We're also working on a plan where German PhD students and postdoc students can come to Indian industry, but that's being worked out, and I think hopefully in a year or two we could convince the German ministry for that. But presently it's one-sided, this program. It's from India to Germany, Indian PhD students and postdoc students being given a fellowship to go and stay and do an internship or work at a German industry. So there are two types of fellowships here. One is the PhD Industrial Exposure Fellowship with the age limit of 30 years, and you can stay up to 6 months at a German industry as a part of your PhD. And there's the postdoctoral industrial fellowship, and you can spend up to 12 months at a German industry. A high demand program, and I'm sure a lot of young PhDs and postdocs here could go for it. And we have already had around 4 success stories from IIT Madras. And maybe I should just show you some of them. These are some of the fellows for the last 2 years, going from very good institutions from India to very good industries. In Germany, it's also accepted if you go to a Fraunhofer Institute, because Fraunhofer works on applied research. So we consider Fraunhofer also possible for this fellowship. So these are some of the fellows, just to give an idea from where they go to where. There's one more IIT Madras here, going to a Fraunhofer lab. This is some map I always put in because it shows how the industrial fellows itself have connected between the two countries. It's not just a connect to exchange knowledge, but I think it's also a big connect for cultural exchange. I think there's a cultural exchange happening through this program, not only this, through every program. So this is some slide I like to show off whenever I say it, because it's connecting India and Germany in a very good way. This is Wiser. Today being Women's Day, it's a great program which we have initiated 2 years ago. It's called Women Involvement in Science and Engineering Research. It's basically to give women lateral entry into projects in the other country. So for example, if there's a woman scientist at IIT Madras and she wants to work on a project at TU Munich, she can work for that project staying at IIT Madras. We'll fund her for the project. She needs to go to TU Munich only once a year for 1 month. And that is also funded by Igstc. So we fund the entire cost for the project. And the German awardee gets 48,000 euros and the Indian awardee gets close to 39 lakhs. So this is both ways. We want German researchers to come to India, women researchers. We want Indian women researchers to go to German institutions, industries. So this is also open to go to industries and work with industries. And this is a high demand program, and we support 20 women researchers every year. Industrial fellows, my earlier program, we support 20 every year there too. So these are some of the success stories. Unfortunately, we didn't have too many applicants from Germany last year. This year, we have already received quite a few applications from Germany. It is improving, our outreach is improving, and I'm hopeful that we'll have more than 10 applications from Germany next year. But from India, it's close to 20%, the success story. There are a lot of good applications coming from women scientists, and these are some of the few who have been selected last year. So they again have really connected across India and Germany. So we're very happy about this. So the spread is good. This is something very pertaining to educational institutes, research institutions, and industries where you have youngsters joining your institution. So this gives a chance for a German and an Indian to connect with each other. It has to be in pairs. We fund the pair together. So it cannot be one-sided, it has to be two-sided. You connect with a German early career researcher. You can ask him to come to your institute here, and you can travel to his institute and explore the research scenario in those areas. So this is more an exploratory. If you have a research idea, well and good, you can connect at a very early career, early age. And this helps you to then apply for network programs like the workshops and 2+2 projects in future. So you have a better connect with your colleagues in Germany, and the German colleagues have a better connect with those in India. So the eligibility is 35 years or below. It's a 2-month fellowship, and it's 2,300 euros per month. And I think that's good enough to be in India or in Germany. So again, a high demand program, and we had very good participation last year. This year, the call is still open till 31st March, and we have already received numerous applications. So we'll fund 20 pairs a year based on the quality of proposals. So this is how they have connected, and I think, again, very well spread between both the countries. So those are the main programs, but if there's something very quick you want funding for, up to 10,000 euros, you want to exchange an idea, or you want to demonstrate a product from industry to industry, this is all the programs are open to industry also. And you want to send a personnel to the German industry, or the German industry wants to visit here, a research lab, and demonstrate a product or talk about a new partnership. We have a small scheme called SING, Small Immediate Need Grants. We'll fund you within 2 months. So this is a quick single window approach. You can approach us with, there are different areas you can approach us on. It's on our website. Let me not go into the details, but I think this is really quick, and a lot of people are applying for this. Success rate is less because we receive too many applications, but we really select those which have a future potential for Indo-German Connect. So that's the way we look at. And these are some of the scientists, industrialists who have connected through this. Yeah, so this is what IGSTC offers. So it's more than workshops, it's projects, it's women scientists to connect, it is industry connect, for early career researchers to connect. So I think we have a very inclusive ecosystem for funding for research, the S&T landscape in India and Germany. So we are hopeful that all of you will spread this news and try to take up these fellowships and offer it to your students, the early career researchers and women scientists at your institutions. And what we are going to come up for the future are these. I told you the next thematic call for 2+2 is going to be on waste to wealth and sustainable packaging. And we are also looking at workshop proposals and women scientists to connect in areas of green hydrogen and AI for sustainability. These might be potential areas for the future to connect between India and Germany. So a lot of achievements, I would say, for the last 13 years. So these are statistics, but what strikes out is I think we have connected close to 5,900 scientists, industry personnel, and young researchers between India and Germany, and more than 330 institutes between the two countries. And many of them are seen here. So it's a lot of institutions, industries between India and Germany, and I think we have made a presence nearly all over Germany and India through IGSTC programs. So thank you very much for listening. I'll be happy to take any questions now or later. Thank you, Ravi, for giving me this opportunity. Thank you.
Can you hear me? Yeah.
Yeah.
Thank you for a nice presentation and to give an overview about the Indo-German bilateral cooperation opportunities. And the presentation is now open for discussion. Are there any questions?
Yeah, I think there's one. Yeah.
So the Chancellor was visiting India 2 weeks ago. Are there any plans for, let's say, to intensify the collaboration between Germany and India in terms of research and science?
I think there was a lot of focus on science and technology. And I think the announcement, joint statement, has actually said that, because I think they want, all the areas what I mentioned were there. And I think they are looking at more of Applied Research Connect also. And I think there has been a little cutting of funds from the German side, from BMBF. But fortunately, they have not cut any funds for IGSTC, except for the 2+2 announcement has been delayed. All the other programs are fully being funded. So I think they still hold the relationship with India in science and technology very high. And I think we are the only center which is getting the entire funds for all the other programs. 2+2 has been pushed for 1 year. Yeah, yeah.
Hi, thanks. How about the fundamental research along with the technology?
So, except for 2+2, where we look at applied research, because IGSTC was set up with an idea of connecting industry and academic institutions and research institutions. But wiser workshops, we can have them at fundamental research levels. I think many of the women scientists are working on some of them going to Max Planck Institutes in Germany.
Okay.
Yeah, yeah.
Okay. Thanks.
Sir, it's applied research, so it involves between the industries, Indian industry and German industry also.
Yeah.
So how the IP rights will be, suppose new technology is developed through this research, how the IP rights will be?
So I told you there's 4 partners and the 4 partners decide. Yeah. So if the IP has come from the German side, I think they would leave it. So we don't play any role. IGSTC does not hold anything on the IP. So we let the partners decide. They sign an internal agreement and they will go by that. Yeah. Yeah.
Are there any other questions?
So far, we never had a problem with the IP. I think the partners have been quite good enough to decide on their own. So, because I said TRL 3, because by that time you already have the idea, and it might have been patented by then. But any new idea coming up, I think they do it jointly, publish jointly, or yeah. Thank you very much. Yeah.
We have one more question.
One small question. How about funding startups from India with startups in Germany? Is that a possibility?
We will fund a startup through the SING if they have something to connect with in Germany, or the German with India. But of course, it has to be a connect between India and Germany. So it will not be a startup which is just doing something in India, but it will be with the German connect.
Okay.
Yeah.
But it is possible that a startup in India can connect with a startup in Germany?
Of course, of course. Industries can connect. They can use any of these programs.
Okay.
The startups can use these programs also. Yeah.
Thank you.
Thank you very much again for this overview about the opportunities of the IGSTC. And we hope we can fulfill the expectations of the IGSTC that many more people are motivated to apply for a proposal and for a project. Yeah, then thank you again for the speaker. And then we can start with the scientific program. And it's a special pleasure for me to introduce you Professor Stefan Schaffhöhner from University of Bayreuth, and he is the chair of the ceramic materials engineering at our university, and besides this, he is also my boss. Yeah. And he gives a talk about the effect of matrix porosity and prepreg tech on mechanical properties and processing of oxide ceramic matrix composites. As we have a lot of, or many topics at our chair, it's a big chair dealing with ceramics, and beside the PDC activities, we have also a lot of activities in the field of ceramic matrix composites, both in oxides and non-oxides. And now I think he gives a short introduction about the oxide fiber CMCs. Thank you so much.
Thank you very much for the nice introduction. So the workshop is about PDCs. So that can be either polymer-derived ceramics, but also precursor-derived ceramics. And something about the chair at the beginning. So I'm at the chair for about 2 years. And as Dr. Mutz was mentioning, we have 3 research groups. One focuses on precursor-derived ceramics, and which is on the left side, and one is deals with powder technology. It's translated, but it's more working. So one of the main focuses, our main focus is on ceramic matrix composites based on slurry-based CMCs. So, and then we have another one that is based on polymer-based CMCs. So, in all 3 of these groups deal with precursors, and all 3 of these groups work with precursor-derived ceramics. And so we have several talks during this workshop, and 4, I think, are from the precursor-derived ceramics group. 1 is from the CMC group, and I give a talk about some research that has been recently published from the powder technology group. Something about the university. So Bayreuth is in northern Bavaria, called Franconia. So the region is Franconia. And so the university was founded in 1975. It's a very young university. It was the youngest university until recently, when there was a new university set up in Nuremberg. And in this new university, we are in the newest building at the moment, so which is called the Tau building, which was opened in 2019, and which is also, let's say, if you look at the campus, we also have a very nice green campus, so you're very welcome to visit our nice campus and also our nice town, and also our nice facilities at the chair. So what is my talk about, actually? So actually coming to research, it's about oxide fiber composites. And for these oxide fiber composites, for the fibers, you need precursor-derived ceramics, but also for the matrix. And today it's more about the effect of the matrix porosity, and also some investigations on the processing of oxide fiber composites, because this is not, let's say, straightforward. So why do we use these oxide fiber composites? Ceramics, everyone in this room, or most of the people in the room know, ceramics have excellent properties at high temperature, but they are brittle, so that's why there's intense research on fiber reinforced ceramics to overcome this brittleness. And the advantage of oxides, on the other hand, is that they are have an inherent oxidation stability, and ceramics, compared to metallic components, they have a low density. So oxide ceramic matrix composites, they are used for environments up to 1,200 degrees Celsius, which is mostly constrained by the fibers. And here we have some examples. One is in thermal processing of metals on the one hand, and on the right side we also see some developments for turbines, and which is actually picking up quite well, especially in the United States developments, but also in France, for example. So at the chair of ceramic materials engineering, there's intense research on ceramic matrix composites, and also for several decades, I have to say, and also some in the last years on oxide CMCs. And so we have the publication actually that is the whole research is based on, because it's here it's described a very nice process, which is very actually quite easy from the raw materials point of view. And we use an alumina zirconia matrix, which is already has been described in literature, let's say 20 years, 15 years at least. And Nextel 610 alumina fabrics, which is, besides alumina 720, the one that are on the market for several years now. So the strength is about 350 megapascal of these OFCs. We have fiber volume content of about 40%. That is the limit. Also in other groups. And we have a matrix porosity, not overall porosity, of 45%. And here you can see the whole process. So first of all, we have the slurry on the one hand, and which contains glycerol as hydrating agent. We have a dispersant, we have a powder, and here we have the fiber architecture, which can be, for example, nonwovens, but also fabrics. We then follows an impregnation. Then we have a conditioning, so that means we have some controlled evaporation of water in order to get the so-called pre-preg tag. And this will also come in this lecture quite often, pre-preg tag. So that means if you have several layers of pre-pregs, then that they stick together and they do not delaminate, which is quite important to have components. This kind of, the pre-pregs, they are laminated, then they are dried, and this can be reversed, like not reversed, but it can be repeated several times in this kind of lamination process, which is shown here below. And then follows the sintering process. And here you can see some of these demonstrators that have been produced in the last years in at our chair. So OFCs, they work according to the weak matrix composite concept. So that means the energy dissipating component in the composite is the matrix. And it's known that the matrix has to be weak, so it has to have a certain porosity, but the effect of the porosity is not well explained in scientific way, actually, and also the limits, they are not explored, and also how to assess the properties of the matrix in the composite is also not well understood. So that's why this was explored in one of our recent publications in Composites A. And the question is how to densify the matrix without actually impairing the fibers, and also not, let's say, having a heat treatment process that actually actually has larger effect than the densification of the matrix. And so the minimum porosity for damage tolerance is not transferable between different composites, so it has to be explored, and also how to do this. It's not has not been described, and so that's why we use zirconium and wood oxide as a precursor, because it's non-harming. And we infiltrated this OFC several times, and then we had a heat treatment at 950 degrees Celsius. On the one hand, the precursor showed its effect because it was decomposed, and on the other hand, it was not damaging the fibers on the other hand. And then we determined the porosity simply by Archimedes, but also then the mechanical properties were assessed later. So here you can see it. So we have for the green body, we had this OFC sample, we had this infiltration. This infiltration process was repeated several times. And then also we had a reference sample to see the effect of this heat treatment, to see if the heat treatment had any effect on the fibers. So here on the right side, you can see the numbers of infiltrations. So we had up to 7 infiltration cycles. And we have here the matrix porosity, so only the matrix is assessed, not the fibers taken into account, which is important because I often get this question, 45% is quite high, the porosity, it's only the matrix, not the fiber component. Here we can see the interlaminar shear strength, which is the strength more or less of the matrix, to say this way. And we also have the 3-point bending strength. And you can see that actually both were decreasing as now. So first of all, we have the submatrix porosity, and we have the two kinds of samples. So one is the 3-point bending samples and also the ILS samples. So we see the decrease of the matrix porosity. Here we can also see this in the microstructure. What is actually seen here, we do not have a significant bonding between the matrix and the fibers, but after several infiltrations, well, this also the matrix is bonded to the fibers, which is actually then impairing the properties later. Here we can see the S-fired samples, so that were the reference before heat treatment. Then we had the heat-treated samples, so that means the samples that were not infiltrated, but were heat-treated, let's say, in total 8 times. And we can see, first of all, that the heat treatment was not affecting the strength. And also we can see here that the interlaminar shear strength, so the strength of the matrix, to say this way, was actually improving somewhat, but actually it was not impaired either way. So also in microstructure, we could also see that the microstructure was still the same. So we can also say that there was no fiber damage using this method, and also the matrix was strengthened due to the heat treatments. This is actually post-processing sintering. So then we see the bending strength, and we can see here as a function of the matrix porosity. And so we have here the shear bending strength. We have here the porosity, which is then decreasing as a function of the matrix porosity. And here we have the strain. So we can see also here these strain strength diagrams, and you can see here the typical damage tolerant behavior, and here also with several infiltrations which the material became brittle. On the other hand, and which is also quite important if you talk with people working on OFCs, one of the most important properties is not necessarily the overall strength, but the strength of the matrix, especially due to off-axis loading. And here we can see that the submicron porosity, and we can see that we had a maximum at about 35% of submicron porosity at about 24 megapascal. And to give you some perspective, so without infiltration, we had about 14 megapascal. And the best values in literature, they have 17 megapascal, which is more or less without infiltration, which is known. And if we have 25% matrix, 25 megapascal of interlaminar shear strength at about 35% matrix porosity, which is actually a very good value compared to other published research, and also to people that we know from industry. Another aspect that I was talking about is one is the matrix porosity and the effect, and that you can change it with these with this kind of infiltration with this precursor. Is also how to assess this pre-preg tag. And I showed you this process, which was repeated several times. And for polymer matrix composites, this kind of so-called pre-preg tag, so that if you have 2 layers, if you stick them together, and if you have a lamination process, you do not want to have this delamination. And how do you assess this actually? And until now, it was a lot of trial and error, and also, let's say, the person who does it and has this domain knowledge. But obviously, you want to have some kind of method to assess this kind of processing. And that's why one of our PhD students, Felix Lindner and Georg Puchers. They put a lot of thought into this and came up actually with this small setup in a typical rheometer, and where we can also investigate this kind of infiltration of the slurry into the fabrics. Here you can see some samples, and here you can see also the typical rheometer curves. And what we found out is actually that these rheometer curves, they are useful, but they are not sufficient to assess this kind of processing. And so that's why they came up with this setup here in the rheometer, which is a plate-plate geometry. And they also use the so-called mini laminate, 30 by 30 millimeters, which is quite small, so it's also quite quick. You can develop new formulations quite easily without actually much with low startup costs. And here you can see these kind of the procedure. So one was, first of all, the total compaction of these laminates, and so which is quite high strength or force, which was then applied, and then we had this relaxation process. And here we have this kind of decompression of these kind of laminates, and which was repeated several times to see actually the effect also of the infiltration into the matrix, but also then the rebound of these kind of laminates. And so we had several steps and also some kind of dwell steps to investigate the time-dependent rebound. So here what you can see here is, first of all, we have one is the real pre-preg. So that means actually the fabric infiltrated with the slurry on the one hand. And also here we are only at this fabric stack without the slurry to see what happens if we compress it, and then we have this decompression. And what you can see here, that the fiber volume content, which is the most interesting graph here, is that if we have the pre-preg and we do this kind of decompression, that actually the fiber volume content stays quite high, but we still have some drop due to this kind of relaxation of the whole system, and which is actually effect of the slurry rheology, which then also affects the pre-preg tech. So what we also can see that this kind of rebound cannot be completely avoided, but it's much less, let's say, than of the fabric stack only. Then also we have, which is, how to say, it was interesting but not completely successful, to have some kind of graphite as space holders and also to see the effect of the matrix. And so here we have this reference material, which is AZ for alumina zirconia, and then we have G, which are different kinds of graphites. And what we can see here, that this graphite, for example, led to more pronounced relaxation process, so we had a larger rebound. And that can be also seen here in the microstructure, that, that actually these graphites, they had a medium D50 of about 10 and 17 micrometers, which is actually quite large for these kind of slurries. So if you want to investigate actually the effect of the porosity in the future study, we have to use space holders, which are much smaller. And also we can see that actually these kind of, they were not actually infiltrating these fabrics quite well, which is then the reason also for the larger rebound. So that shows already that this kind of infiltration has to be into the fabrics, has to be optimized, and also the interaction of the fabrics with the slurry and also the wetting behavior has to be investigated in order to avoid this kind of rebound, to improve this pre-preg process. So that means we actually we have different effects of particle sizes of the slurry. We also have different effects and over superposition of this tech, and also this slurry squeeze flow. And if you go back to this slide with the rheology here, we, for example, can see that actually we have a shear thinning behavior with a very high yield stress, which is actually the optimal behavior, which can be also optimized by some kind of additives. So then the question is always, if you have some kind of small laboratory setup, how does this then behave in, let's say, in the scale-up? And so we have here this lamination process. We have this fiber volume content. If you have the testing method, actually these with the testing method it was always somewhat higher, so we have a systematic error, but it was very much actually in the range for the lamination process. So that means actually the setup for testing these kind of these laminates was quite accurate. And so we then have for the, it's very suitable. It also is important for us to develop new systems for new OFCs, and also we can also compare different kind of fabrics in the future, and also to investigate the effect of the matrix porosity using this kind of precursor-derived ceramics. So I would like to thank you for your attention and come up with a short summary. So these OFC fabrication at the chair of ceramic materials engineering is very simple, but also simple on the one hand, but also if you compare to other processes known in industry, actually it has very good properties. The porosity can be adjusted by optimizing these kind of properties, the porosity. And the porosity limit in case of our system is 34%. And now the question is, okay, what are actually the mechanical properties of the matrix, which is coming up in another publication, and which can be then assessed by this kind of precursor infiltration. And on the other hand, the upper porosity limit, it still has to be determined by using some kind of better space holders. So thank you very much for your attention, and I'm happy to answer questions.
Thank you, Stefan, very much for this very nice presentation. And now we have time for several questions.
Well, thank you, Professor, very much for the wonderful presentation. Just want to, I have twofold question. Want to know that what are the advantages of oxide fiber reinforced composite over non-oxide reinforced composite? Number one. And number two, we understand that you develop the matrix by alumina zirconia. So how did you maintain the submicron grain size upon sintering?
The last part of the question I didn't get.
How did you maintain the submicron grain size after sintering?
The submicron porosity?
Grain size.
Grain size, yeah. Yep. So, answer the first question. First of all, the fibers, the oxide fibers, they are not cheap, but they are much cheaper than silicon carbide fibers, for example. So it's more or less an order of magnitude at least. So this is one aspect. The other aspect is the inherent oxidation resistance. So you do not need any EBCs, at least, let's say, in an environment, at least in an environment where you do not have too much water. Yeah, so this is one aspect. The other aspect is, for example, the processing. So if I showed you the processing, for example, you can use typical, let's say, established techniques known from ceramics to just infiltrate this kind of matrix. So which is also much faster and also much cheaper. So this is actually, I think, for industry, not, it's quite relevant. The other aspect is the grain size, which is a very interesting question. And actually, it's, that's why we use this kind of matrix. Because zirconia, we have about 20% zirconia in the matrix, which then, it slows down the grain growth of alumina quite substantially. So actually, it's interacting with the alumina to, that's why it hinders the sintering actually of the alumina particles. So there are other ways to do this. I mean, like Bremen, for example, has published
on this topic to add some other additives. But zirconia is known. I mean, like it's known from other fields as well. Let's say dentist ceramics, for example, as well.
Yeah, thank you very much, Stefan. So the goal is to have a tough matrix and a weak interface. So do you think it's possible to have a kind of gradient? For example, in porosity, so porous interface and less porosity in the matrix, or playing with residual stress? For example, tensile residual stress at the interface and compressive in the matrix or something like this?
Well, at least this kind of gradient, we had discussions about this recently in a PhD talk, how to actually have this kind of a gradient, and also how to say, first of all, you have to assess the properties correctly. That's our first goal, to have these, because if you have only the matrix, for example, and if you make monolithic samples of the matrix, you have the problem that you have the shrinkage. So, I mean, like you know constraint sintering quite well, and so the first aspect is to take the constraint sintering into account, and then to think about, okay, what's the effect of the constraint sintering actually on the interaction between the matrix and the fibers, for example. We have not thought about having the internal stresses actually as one aspect. We have not thought about it yet.
But if we look at the microstructures with infiltration, finally, perhaps you might have with constraint sintering some tensile stress at the interface and more porosity, but finally you feel it with the precursor, and then you don't have it anymore.
Yeah, sure. I mean, like I actually came up and I gave. So we had this talk the week before the workshop actually, and I actually gave your publication on constraint sintering, the thin film. And you mean this one here? Yeah, and this is the typical. And when I saw this, and I said, actually, this is constraint sintering at the interface more likely, because this one is not sintered, because it's more or less already dense.
So rigid.
Yeah, and it's rigid, and this one here is the one that is actually then it's sintering. Yes, and here actually you have this. You fill it up actually.
Yeah. We can discuss later, but I think it's important. Yeah.
Yep.
Another question?
So thank you very much. It's a very interesting presentation. So I have two questions. One is with respect to the interface. What is the order of this interfacial bond strength between the fiber and matrix? Or rather, I can ask this, what is the ultimate fracture toughness you got? The second one, did you study the creep behavior of these composites?
Okay. So first of all, the fracture energy here at the interface you were asking. So this is quite difficult to assess, first of all, especially if we have this kind of weak matrix composites. So there is a lot of research done in Bremen again, and for example, you can use a push-out test or push-in, depends. It's not so easy for these kind of weak matrix composites. We are in the process of buying a nano indenter, and this is one of the tasks which is on our table for the future. Especially for this system, because it's our own system, because we are able to produce our own samples. For, let's say, weak interface composites, it's easier. It's not easy, but easier. And so the second part of your question was the creep behavior. So I showed you the temperature limits here, 1,200 degrees Celsius, which is quite optimistic for alumina fibers. Alumina fibers, 1,050 degrees Celsius. Mullite fibers, 1,200 degrees Celsius, but the strength is lower for mullite fibers than for alumina fibers. High strength, alumina fibers. higher creep resistance, mullite fibers. Both available from Nextel.
One more question, Ravi. Oh, okay.
Okay, sorry. Hi, it was a nice presentation. My question is about the slurry that you have prepared. Is that in the crystalline form, both alumina and zirconia, or these are in the precursor form?
They are crystalline, but they have very small grain. Depends on who you ask. Very small, right? So the D50 for one of them actually is in the submicron range, so about 500 micron and nano, and then the other one is 100 or 50 nanometers of the which is the D50 of these oxides, but which is only 5% on the matrix.
Yeah. And what is the solid loadings of these? Solid loadings. Solid loadings.
So they're slurries. Yeah, they're.
What is the percentage of
the so you mean the solid content in the slurry? My guess would be from processing, if you have certain rheology, let's say 50% would be more or less the solid content, maybe 40.
Thank you.
Yeah. Ravi, do you have a question? Okay.
Have you done long-term oxidation studies on your samples? And do you have any open porosities in your samples? That is the first question. Second question is, you say 34% of porosity is required for damage tolerance, if I understand correctly. Around 34%.
35%.
Around 35% porosity. So how much of compromise on strength do you make by having 35% of porosity?
In terms of
strength compromise in order to make sure that your material is damage tolerant.
So let's say, first of all, the question was long-term. The oxidation is not a problem. The problem is water. The problem is water and also other environments. I mean, like they are kind of nasty environments, and even like small amounts of sulfur, for example, is known to have some kind of negative effect. So, for example, for metals and also other ceramics, it's known that sulfur, for example, is not quite good. We have not investigated it. Let's see if the funding agency wants us to investigate it. Yeah. Then second question was the compromise. Yes, it's a compromise. For these kind of CMCs, it's always the porosity. And there has been research on dense OFCs, but they are not successful until now. The question, so this is a problem actually for these kind of materials. And there are also discussions in Germany about how to overcome this kind of problem. And so at the moment, to have damage tolerance, 35, how to say, this was the best value actually, 35% of matrix porosity. You can have lower, but then you have you impair the damage tolerance for our system. But first of all, you have to assess it, then you can improve it. That's the approach at the moment.
Okay. No, I would like to stop the discussion and to shift the discussion to the break, because we are in time. And Stefan, thanks again for your nice talk and for the discussion. And please stay on stage, because you will receive a gift that you remember the workshop.
And I want to have my presentation in the back. Okay.
I request Professor Ravi Kumar to hand over the memento to Stefan, sir.
Thank you very much, and we are very good in time, so I hope everybody can enjoy the tea now, and we will meet us again at 11.
Just before going for tea, please come for a group photo here. We take a group photo and then we go for the high tea.
Okay.
The high tea is just adjacent to this room, but let's meet quickly for a group photo.
I request Professor Ravi Kumar to hand over memento to Gunther sir for being a great session chair. Okay. Yeah, I request everyone to come for the group photo. So few people will be coming on the stage and few people will be standing below the stage. And before going for the high tea, I would like to tell you we have kept the food coupons in the front pocket of your bags. So whoever is not having the food coupon can get it from the registration desk. Okay, thank you. So maybe from front.
One more layer is there.
I request
Welcome back, everyone. Please be seated. So, we shall have the next session of the day. It is titled Precursor-Derived Ceramics for Energy Applications. So, I request Shyamrao sir to take over the session. So, one small instruction. The talk will be for 20 minutes and 5 minutes will be for discussion. Because of time constraints, I request everyone to just stick to the timings. Thank you.
So good morning. Welcome to the session on precursor-derived ceramics for energy applications. So we have 3 keynote lectures in this session and 1 invited talk. So the first keynote lecture will be delivered by Mr. Olivier Guillon, Director, Institute of Energy and Climate Research at FZ Julich, Chair of Material Synthesis for Energy Technologies at RWTH, Aachen University, Germany. So he will be speaking on precursor-derived functional ceramics through reactive sintering. I welcome Mr. Olivier to deliver the talk. Olivier, over to you. Thank you.
No? Ah, yes. No, I can hear me too. And we need just to change the slides. Because this is not my presentation.
Oh.
Perfect. Okay, yes. Thank you very much. And thanks to the organizers, Javi and Günther, invitation and this wonderful workshop. It's my great pleasure to be here today. And so you can see here a picture of our campus. It's a green campus, although today it's white because it's still winter in Germany. But I think there are quite a lot of similarities between Jülich and IIT Madras. We have a forest, deers, rabbits, beavers. We have no monkeys, but we are in the middle of the nature, and it's also very, very interesting. So here, a brief presentation of the research center. So Forschungszentrum, it means research center in German. It's part of the Helmholtz Association. It has been mentioned already before. Founded 3 years before IIT Madras, so about the same age, at a nuclear research center at that time. And the funding comes from 90% of the Federal Republic of Germany, so like IITs, finally. We have 11 institutes, more than 7,000 people working, and Jülich is a small city, but with a lot of international links, and we have also, of course, people from India. Our fields of research, information, so supercomputing, neuromorphic computing, quantum computing, bioeconomy, plant-based value chains, and energy, renewable energy, and also a link to the climate to atmospheric research. So from a holistic point of view, and this is my field, energy research. And in my institute, we look at we are mission-oriented, so we are looking also like IIT on solving big challenges. And one of them, of course, is energy supply. And for this, materials are very important. And we focus on ceramic-based layer system composites for energy technologies. Here you see the 4 main applications we look at. High-temperature materials, ceramics are the best choice, the unique choice
for this type of application, gas separation membranes, solid oxide cells, and all solid-state batteries. And this is the topic of my talk today. Due to the time, I've decided to focus on one specific application and focusing on oxide functional ceramics. Before we heard about oxide structural ceramics. Now we are talking about function in batteries, and also not polymer-derived ceramics, but precursor-derived. Okay, so where are oxide ceramics useful in batteries, especially solid-state batteries? So here you have the sketch of such a battery. You have the separator here in the middle, which is in that case a solid oxide foil, separating then the two electrodes. So you have the negative electrode, the anode. It's hopefully a very high capacity anode, pure lithium metal or sodium metal, if you think about lithium or sodium battery, or an alloy. On the other hand, you have a cathode. The cathode active materials already in your batteries, these are oxide ceramics, powder, very, very advanced powders and morphologies. And in solid-state batteries, then this is mixed with a solid electrolyte in order to provide the ionic transport through the cell. So oxide materials, especially electrolytes, are used in different places, fulfill different functions in a battery cell. For the separator, you see, for example, you need high ionic conductivity so that the ion can transfer quickly. Otherwise, you cannot charge it or discharge the battery at high speed. Here, on the other hand, you have a composite layer, and the material, the problem, they both, of course, contain the mobile species, lithium in that case, for example. And if you take LLZO, this is an electrolyte. It's quite stable at high temperature. And the cathode active materials, it's usually less stable already. But if you mix both, then they react with each other at a rather low temperature. So if you want to co-sinter this at temperature, you will get problems. They will react, and your layer, your composite layer, won't behave properly. On the other hand, it's one strategy can be independently of the electrolyte used. It can be solid, it can be liquid also, to use a coating in order to protect the cathode active materials from dissolution, from reaction with the electrolyte. And this is also where oxide thin layers can play a role. And that's the topic of my talk today, this thing and this thing. And that's also to show that a precursor-derived route can be quite interesting from that point of view. So precursor-derived protective coatings on cathode active materials for lithium-ion batteries, and here infiltration of porous electrolyte network by a precursor solution and in situ synthesis in the porous network for sodium solid-state battery. So I hope you can get a flavor of the topic. So protection of cathode active materials is not new. Depending on the composition and also the electrolyte, already in commercial batteries, you need a protective coating. But the question is, of course, how to apply homogeneous thin film coating on this powder material. Here you have some spinel, here some layered structure. You see nickel, cobalt, manganese. It's a short NMC cathode material. It's an oxide. You have, of course, the, let's say, precursor-derived vapor-based route, so CVD, ALD. This is possible to deposit. Otherwise, you have also some synthesis of nanoparticles. Here, the problem, how to get the full coverage and homogeneous coverage here. So one approach we decided to test, knowing from the literature and our colleague at ETH Zurich, Markus Niederberger, there is an interesting soft chemistry route, microwave-assisted synthesis, using some precursors, here acetate, acetylacetonate of the metals, mixed with benzyl alcohol and reacting in a microwave reactor, very low temperature, 200 degrees C, and very short time, a few minutes. And with this, you get very well defined, dispersed nanoparticles of the single oxide. So With this, you can go fast. It's a uniform controlled process, increased reaction rate, reproducible, so nice. But what about adapting this concept, this route, to produce a coating on already synthesized powder? So that's what we tried. And here, so it's a modified route, and the coating of our choice is aluminum doped zinc oxide because it provides different properties. One of them is also electronic conductivity and so on. Already mentioned NMC 111 because we have the same amount of the three cations. So we put the powder in this solution, microwave it, and then get hopefully a coating. This is the simple idea behind. And now you can see before coating and after coating, an example. You see the temperature below 200 degrees C, very quick. And it seems we have a nanoparticle here on the surface fully covered. Now let's look at a few more details. We did some deeper investigations, modifying the concentration here of the precursor solution, the time, the temperature, and finally this is also the amount of the zinc oxide layer deposited. And here you see, so depending, so if for example, we increase the concentration, we have much thicker coating compared to here. If we are not high enough in temperature, we do not crystallize the layer. So it's an optimum, but you can see here V1 highlighted, V3, they are not that bad. So we focused on the properties afterwards. So first, are these layers crystalline? Yes, indeed, you can see here NMC and zinc oxide pure, and then we cannot find really additional reflexes. So it's well crystallized coating without any reaction with the substrate, which is also very important because this otherwise might impede the transfer of the ions, the charge transfers at the interface. And, here, a few examples. Then, so V0 is a reference, the bare NMC uncoated, and here the two coated materials. So yeah, this is specific to battery research. Discharge charge as potential capacity. You see that perhaps the easiest graph is here to look at the rate capability. So you measure the discharging of a battery according to a C, right? 1 C, it's a 1 hour, and then you divide it, so it's slower. 4C, yes, it's 60 minutes by 4. So, and so what you can see, nevertheless, is if you are uncoated, these are the circles here, you have a degradation. The quicker you charge or discharge your material, the quicker, the lower the capacity. So it's unfortunately very often observed, this phenomenon. But now we see with the coating, especially V1, we have hardly any dependence. So the explanation, most of the time, is given by a lower polarization, which means a lower interface between the cathode active materials and the electrolyte. So this coating has a good activity, enables a good transfer. And here, during cycling, you can see also that with the coating, we have less, so first, higher initial capacity, more lithium ions can go inside and outside, and also the degradation rate is lower. So stabilization, in this is a liquid electrolyte environment. The question is, in solid environments, what would be the behavior, and needs to be adapted anyway. So this is an example, a precursor based derived route for a functional coating for stabilization of cathode active materials, published here in Nano. The other part of my talk is based on all solid-state batteries, sodium based. For this, you need electrolyte, mentioned here, with a conductivity of 1 millisiemens per centimeter at room temperature. And good news, there are some candidates. For this phosphate material. It's a Nasicon material. Nasicon means it's a sodium superionic conductor. Polycrystalline material, also a real ceramic, not a single crystal. No? Then it is very stable from a chemical thermal point of view, electrochemical point of view too, so that it's anyway solid, safe, but also compatible with the metal anode. This is very important. Does not decompose in contact with the sodium. It has, as a ceramic, a high mechanical strength. Points to clarify or to improve processing, high temperature sintering. If we want to make a battery, reaction with the cathode, active material, and yes, compatibility with them. So reactivity means high interfacial resistance. We have seen before in the last example why these interfacial resistance are very crucial for the performance of the battery, and also in order to get a low degradation during cycling. So a few words about the material. So electrolyte, yes, I knew I have more details. So, this is this formula. So there are no critical elements in it. You see very abundant materials. We developed a synthesis route, a solution-assisted solid-state reaction to get a high-quality powder. This is the crystalline lattice, the unit cell of this NSZP, and the cathode material, it has the same structure. This is also Nasicon. It contains vanadium to offer electrochemically activity. And the anode is a sodium metal. So we built a full inorganic cell based on those materials. And of course, you remember design of the cathode. Yeah? So there are two routes, in principle, at least two routes to approach. So here we have the separator, should be dense. Then we have the mixed cathode. One way is mix the powder co-sinter. So this is the traditional route. Unfortunately, you need really high temperature, above 1000 degrees C, 1200 degrees C, where also the cathode materials decompose already alone. And there is the other route, so a porous scaffold infiltrated by a precursor, and to build in situ the cathode active material. And with this, what are the advantages? Large contact area, small particles of the cathode materials, continuous pathways for both electrons here and ions through the electrolyte, higher tolerance to volume change. One has to know that during charging, discharging, there are huge volume changes. For this material, it's only 8%, but 8% for ceramic is already huge. And for some others, there can be hundreds of percent. And it's inspired from the fabrication of solid oxide fuel cells. We have been working, the community also, for decades on this, and we know it can work. So now the route, so produce first a bilayer, so the dense separator, and then a porous scaffold. So we mix for this to get the dry porosity, some rice starch, that we sinter and burn in air. Then we infiltrate the porous scaffold with this precursor solution. You can see here the composition. In water. And then after drying and several infiltration, we treat it in reducing atmosphere, rather moderate temperature, 740 degrees C. And then it builds the desired NVP phase plus carbon, which comes from the decomposition of the precursor. And indeed, this is very good because carbon is used most of the time as an additive for electron conductivity. And then we add a sodium anode layer and we test the battery. What is very interesting is that this infiltration works quite well. You can see here a cross-section. So this is the electrolyte. And here we have the cavities, the open porosity filled, not completely, but partially with NVP. And what is really amazing is through this process, you can see here the interface between electrolyte and electrode. Before cycling, after cycling, there is no crack at all. And there is some ion exchange. We have measured this, but it's not detrimental to the mechanical and the electrochemical performance. So it's quite amazing. And we measured by XRD in operando the battery works, the material is active, and we have some deformation, also constrained deformation at the interface. Yes, almost done. Thank you very much. So here you can see the cycling behavior. So a lot of cycles, 100. And here also, very interesting, the cyclability. Now you know here, 1C, a small degradation, but this is actually a huge success at this stage because this battery works, although quite thick for the moment. It's because of the very low internal resistance between all the contact between the particles. And here, this is how the battery cycles. Here, this would be with a liquid electrolyte, and here, these are the other attempts, co-sintering or lithium or whatever. So, and also what is very interesting, we don't need any pressure or temperature control. This works at room temperature. So we are working further on this, but this was one example, a further example on this precursor-derived synthesis. I have no time to talk about reactive sintering. This is also very interesting. Papers to come on different materials on oxide ceramics. It's attractive in order to reduce time, energy, cost, because one big disadvantage of ceramics are the high cost for production, the thermal treatment, the sintering. And if we can find route approach to reduce this massively, there will be new opportunities for sintering. And this enables the powder sintering, synthesis, but also to coat materials powders, like, for example, these cathode materials, which are moisture sensitive. It's to protect them from environment. And all solid-state batteries by chemical infiltration shows very interesting properties, and we are working further on this. Lithium, sodium systems in order to increase the capacity and to optimize the cell geometry. With this, I'm at the end. Thank you for your attention. Happy to answer any questions.
Thank you very much, Oliver, for the very interesting talk on the nano coatings, crystalline nano coatings for the solid state batteries and also the chemical infiltration. So we can take a couple of questions now, if there are any. Yes. Please. Yeah.
Yeah, thank you for the talk. Just a quick question. Your zinc oxide or aluminum doped zinc oxide, what was the precursor used? Did it already have aluminum in it, or did you use two separate salts?
This was two separate salts. Yes.
So how do you control the
zinc acetate and aluminum isopropoxide, if I remember well, and it was mixed, and this in dissolvent, and it reacted in situ.
Okay. But then how do you control how much aluminum gets doped within the zinc oxide? Or?
Well, we use the, let's say, for the precursor, the nominal composition. Let me check. I think in the paper, we have measured the aluminum and the zinc content. What we targeted, but I don't remember all the details, but yes, we could check in the paper. The aluminum and zinc have been quantified by ICPO, yes. So, but I don't remember exactly the exact amount. If it varied between coating conditions or not.
Okay. Just one last question. People also use AZO for transparent conducting applications. Mm-hmm. So did you also do any electrical measurements?
No.
Not really.
Not really.
Okay. Thank
we
you.
were just targeting this application and haven't looked at any other. Yeah.
Thank you. Thank you very much. I think we'll take one more question.
Yeah. I have two questions actually. One is, can you please tell me about the separator that you use? Usually in lithium-ion batteries, we have the alumina-based separators now, alumina-coated separators, and how that is different from your separator. That is one. And the second question is, how feasible is your process, the microwave solvothermal process, to scale up?
Yeah. Okay. Yes. Thank you very much. So separator. For the test here, with the liquid electrolyte, we use a conventional separator. I think it's polypropylene separator. So basically, you have the non-woven, woven, and also including some aluminum particles for high-end. They are more expensive, but these are only inert ceramic particles fixed, embedded in an organic separator. So this is not fully ceramic separator for the moment. What we target for is a fully ceramic separator. So I have no time to show, but there is a lot of processing know-how also for the ceramic community. So tape casting, for example, is a very useful technique to get layers, separator layers, for example, of between 20 to 40, 50 micron in thickness. And we have done some work, published this, but I have no time to discuss on this. The other point, it was on microwave synthesis. It's scalable, and I cannot disclose with which company we are working, but a cathode active material company, and the study is to evaluate the suitability of this method on their material and the scalability. For the moment, we have done this on a small scale reactor, but it's possible to enlarge it.
Thank you very much.
Just a quick question. Can you comment on the sodium ion migration in those cathode materials that you have? The sodium ion migration.
Yes.
Can you comment on that, like how fast they are or how slow they are in those new cathode materials?
Yes, the ionic migration, so it's directly linked to the diffusion coefficient of sodium in the structure, and finally
so how
the
faster,
conductivity.
Yeah, how faster they are or how slower they are in comparing to the benchmark sodium cathode?
Yes, so this is, that's why I gave the 1 millisiemens per centimeter value. This is a minimum for electrolytes, and the sodium ion conductors, the ceramic, the Nasicon, for example, the best ceramic we get for the moment, 4 to 5 millisiemens per centimeter at room temperature. So the liquid electrolytes, they get up to 10 millisiemens per centimeter at room temperature, but liquid electrolytes, they conduct everything. So the transfer number is low. For Nasicon, they conduct only sodium. So transfer number is equal to 1. So we think, at least for sodium, these materials are very suitable to build batteries. And otherwise, the mechanism is simply diffusion. I showed the structure, so you have vacancies, and the sodium ion, they hop from one.
So is there any way that you can enhance that diffusion?
We have done a lot of things on materials substitution development. I believe perhaps some persons, perhaps 20, perhaps 50%, but not order of magnitude. I don't think so. But we are, as mentioned, we are already in the suitable range of conductivity. So,
okay, thanks.
Yeah. Thank you very much, Oliver. Thank you for your excellent talk and responses to the questions. We'll now move on to the next invited talk by Mr. Abhishek Chowdhury, a scientist at Center for Materials for Electronics Technology, India. He will be giving his talk on hierarchically porous silicon oxycarbide ceramics from precursor polymer for energy storage application.
Sir, one second.
Yeah.
I request Professor Günther to present the memento to Professor Oliver.
Over to you, Mr. Abhishek.
Yeah, thank you. You can use pointer.
Yeah, very good. A very good morning to all of you. At the outset, I would like to thank for the invitation. I would like to thank Professor Ravi Kumar, Professor Gunter Moos, and I'm really very happy and privileged to be part of such an Indo-German workshop where I would like to share my research work on PDCs, basically in porous PDCs. I think last time I attended a PDC conference, it was in VSS Trivandrum. Ranjit sir was organizing, he was the convener at that time. So it is good that occasionally we get the chance to showcase our research. So I'll be talking mostly on hierarchically porous silicon oxycarbide ceramics, these works that I have already carried out during my doctoral studies at NIT Rourkela, Orissa, India. So let me take this opportunity to say a few things about my organization where I currently work. I am from CMET, it's a Center for Materials for Electronics Technology. We have 3 labs in Pune, Hyderabad and Thrissur. I am basically from Thrissur. So all these 3 labs have been coordinated by Ministry of Electronics and IT at New Delhi. We have a small group of scientists, 13 scientists, 12 admin staff and 8 admin and finance staff, taking care of all the sponsored projects that we carry out in our work. These are the thrust area in which we are currently working on, renewable energy, sensors and actuators, electronic packaging, nanomaterials. So we work on plasmonic biosensors, we work on piezoelectric materials, thin films. I would like to mention here that a wearable device for cancer detection. This was one of the prime work that was done by one of our scientists. They could develop a wearable device for detection of breast cancer in women in the early stages. And that could help for the woman to go for the diagnosing at an early stage so that it can be treated at early. These are some of the products that at the CMET we have developed. We work on we prepare microwave substrates, BMT resonators, thermal sensor, thermistors. We have developed graphene-based, quickly rechargeable emergency lamp. We have microwave absorbers. We have transparent heaters. We have graphene-based film for which can act like a speaker as well as it can work as a microphone. We are deriving carbon and graphene-based aerogel for supercapacitor application. So here is my plan of my talk. I'll be basically introducing the topic and then I'll be focusing on macroporous SICO, and then I would like to show how hierarchy can be introduced in SICO ceramics. And then we can nanostructured SICO, and then we'll show you how it can be applied for energy storage application, basically in supercapacitor. So yeah, we all know about this SICO, that PDC route have very good potential to be applied in supercapacitor for gas separation membranes, for anodes, for lithium-ion batteries, for gas turbine engines. Various CMCs are used. These are the application areas of porous ceramic. Depending on the kind of strategy that we choose, we can tune the porosity, and we can show that different grades of porosity can be generated by choosing a particular synthesis strategy. So this graph shows the different kinds of porosity, pore size, and their application. So yeah, these are the different methods for generating porosity. We have sacrificial methods where we use a sacrificial macro beads mixed with pre-ceramic polymer, and then we mix and cross-link and paralyze to get a porous PDC. In this blowing method, we have some direct blowing gases are blown in the pre-ceramic polymer mixture, and then it is cross-linked and paralyzed to get a porous PDC. So the trapped air bubbles act like pores, and they generate porous PDC. In the PP mixture, we have two different pre-ceramic polymer having different ceramic yields, giving rise to different kinds of porosity. So we can generate mesopores by using this method. In etching method, we can generate nanoporosity. So yeah, here comes my motivation. So when I started my PhD, maybe some 6-7 years ago, I thought that why can't we introduce a highly open porosity with a good mechanical property. So if you see, the sponge replication method offers a very simple and cost-effective method to generate very high open porosity in a ceramic. But the disadvantage, you can see, disadvantage lies in this hollow struts. So because of this hollow strut, the mechanical properties are generally poor. Whereas in the case of direct foaming, we get generally closed cells. So we get dense struts in case of direct foaming methods. So I thought to combine these two methods, sponge replication and direct foaming method, to generate very high open porosity cellular ceramics with the porosity of above 90% with very strong mechanical properties. Yeah, these are the various silicon containing pre-ceramic polymer. I have worked basically on silicon oxycarbide, porous silicon oxycarbide ceramics, so I'll be discussing only on those silicon oxycarbide ceramics. So if you see in the inherent limitation of this PDC, that we have shrinkage of close to 50% normally, and it generally results in the formation of pores. So it is very easy to develop porous ceramic from PDC route rather than dense ceramic. Although it is possible to develop dense PDCs also, but fabricating a porous PDC is comparatively easier than dense PDC. So here I discuss about the macroporous SICO. So we take a PU sponge template with 80 to 90 ppi, and then we coat the PU template with the pre-ceramic polymer solution, and then we cross-link and paralyze in innate atmosphere to generate macroporous SICO. So it's a very simple route. It's a cost-effective route. But here, like if you can control the cross-linking temperature, we can change the cross-linking temperature, then we can generate porous SICO with hollow struts as well as with dense struts. Basically here we are playing with the thermal decomposition of the PU sponge. So we have got the confirmation of silicon oxycarbide through EDX analysis, and then we thought that whether it is possible to increase the strength of this PDC by suitable increasing the initial viscosity of the polymer. So we could see that if you are having a hollow strut, like if you are having a porosity of 90% and a hollow strut, it will be giving a compressive strength of 0.2 to 0.5 MPa. But when we are having, when we are increasing the solution viscosity, keeping the rheological property constant, without changing the rheological behavior of the pre-ceramic polymer solution, we could enhance the compressive strength from 0.2 to 0.5 to 2 megapascal. So it is not a very, very big enhancement, but yes, we could show that the mechanical property or the compressive strength can be enhanced if you are changing the rheological, changing the initial concentration of the pre-ceramic polymer. So this is basically the specification of the PO form that we have developed. And we tried to characterize the PO form by 3D technique. We wanted to see how the uniformity of struts is there. So we could see that the dense struts could be formed. So earlier we have shown through microstructure, yes, hollow struts were there or dense struts were there. So now we got the confirmation from this tomography that yes, dense struts are present in the sample. And as already I have told that the thermal property or the mechanical property can be enhanced by single technique, by simple single step processing. So here I go to the next part of my talk, that were how the advanced technique for to characterize porous materials. Generally, tomography method is used for composites, where we have different polymer and filler phases, matrix and filler phases. It is difficult to apply the same methodology for porous sample where we have above 90% porosity. So we have to design the algorithm to suit the requirement of our porous ceramic, and then we characterize all the porous structural parameters like. So this is basically the technique that I have used at RRCAT Indore. So it is sample dimensions were 5 to 5 by 8 mm. So smaller samples, representative samples were taken for analysis. So this is basically a standalone technique for characterizing internal features of the sample without breaking it. These are the quantitative information that we derived by synchrotron X-ray source. We found that pore size distributions are very uniform, around 300 to 400 microns. The cell size were very much in line with the reticulated ceramics. We see the porosity variation. We have, when we are making a reticulate ceramics or a cellular ceramics, we see the porosity only from bottom to top. So in this case, we have seen from outside to inside of the sample, and we see that the variation is only of 3%. We get porosity of, or open porosity of 88 to 92%. So very high porous samples we could prepare. Second is the sphericity of pores that we found out by the pore shape, and it comes around 0.7 to 0.8. This is very close to the very close to the sphericity value of tetrahedron cells. And then since it's a reticulated ceramics, we have the pore orientation around 90 degree. Next, I go for the hierarchical porous SICO. So here what we do, we have a very simple methodology where we utilize catalyst-assisted pyrolysis together with the sponge replication technique to develop 1D nanostructure on macroporous SICO. So we can use transition metal catalysts like cobalt, iron, nickel. We can use simple techniques like we prepare a mixture solution where we have a nickel nitrate or cobalt nitrate or iron nitrate dissolved in a pre-ceramics polymer solution, and then we coat the PU sponge template, and then we cross-link and pyrolyze it. So by doing this, we could generate 1D nanostructure on the surface of the macroporous. So this 1D nanostructure which is present on the macroporous bodies will enhance the specific surface area, and it will lead to the hierarchy of pores by crisscross of this 1D nanostructure. So these are methodology is very simple. Earlier I was coating PU sponge on directly pre-ceramic polymer solution. Now I coat the PU sponge template with pre-ceramic polymer solution containing cobalt, iron or nickel. So here, due to time constraint, I will be showing only the results for nickel concentration. So we can see this with increase in pyrolysis temperature, keeping the concentration of the nickel constant, we have used very low concentration of nickel to generate 1D nanostructure. So with this pyrolysis, with increase in pyrolysis temperature, you will see up to 1200 degrees centigrade. There was no decomposition. That is a common thing. Like in SICO, up to 1200 degrees centigrade, then the phase decomposition doesn't happen. Once we go above 1200 degrees centigrade, that is 1300 degrees centigrade, we saw the formation of 1D small, up to few micron 1D structure were observed on macroporous bodies. Now, if you increase further up to 1400 degrees centigrade, then we could generate more volume of 1D nanostructure, and this increase in the 1D nanostructure resulted in the surface area enhancement. So it required to analyze the 1D nanostructure that we have developed, and then we could see that the 1D nanostructure has a spherical tip at the end, and we have a stem. Now, if you look into the TEM analysis of this CAPSICO derived 1D nanostructure, it had a spherical tip which is having a different shade. That means it is having a different mass absorption coefficient. And then we see the EDAX mapping. We could see silicon is present throughout the sample, throughout the stem. Oxygen is present only on the stem, not on the bulb, and carbon is present little bit around the edges. And we see nickel is present only on the tip of the 1D nanostructure. So we could see that the tip could be nickel silicide tips, and we are having silicon oxycarbide system, so we are expected to get amorphous phases in some of the areas. So this is confirmed by this diffraction pattern. And we could also observe the nanoparticulates or nanoprecipitate of silicon carbide on some of the regions of the stem. This also was confirmed by the TM. So yes, we could say that VLS growth mechanism was responsible for the growth of 1D nanostructure. We could also see a formation of an amorphous layer on the tip of the 1D nanostructure, where we could see the formation of graphitic layers. So these graphitic layers also are developed during the pyrolysis process. Now, when we have a 1D nanostructure, we said that the surface area will get enhanced. So this is the BET isotherm for a sample without any nickel, and then when we include nickel in it, that the width of the this hysteresis curve is increasing. So it shows that the mesoporosity is enhanced, or mesoporosity is increased when we are increasing the nickel concentration. So this was our proposition, that when we have a pore without any 1D nanostructure, the surface will be occupied only by the gas absorption molecules. When we are having a 1D nanostructure on the macroporous body, then the surface area would be enhanced, and these adsorbent molecules will be on all the 1D structure. So although the surface area we could enhance from 5 meters square per gram to 13 meter per square gram, but the contribution of mesopore volume or the macropore volume was bigger compared to without any nickel. So yeah, this is the specification of the SiO foam. So because of this 1D nanostructure grown on the macroporous body, the compressive strength gets generally weaker. So this is the side where it is a little bit poorer in terms of compressive strength. Although it can be enhanced if you are, this work can be carried out if you are controlling the amount of nickel or amount of transition metal catalyst that you are using it in our system. Next part, I will be discussing about the nanostructured SiCO. So this is a another technique where we could generate hierarchically porous SiCO ceramics by a simple technique where we take a soft template like nanocarbon, and we try to coat this nanocarbon using pre-ceramic polymer. So the cross-linking and pyrolysis will result in the formation of a porous coating on the nanocarbon. And to further enhance the surface area, what approach we have done? We have done HF etching. So basically we etch out silicon from the system, and we have a carbon derived oxycarbide system. So this is the BET surface area and the pore size distribution along with the TEM. We could see that if you have only nanocarbon or pre-ceramic polymer pyrolyzed at 1000 degrees centigrade, the surface area is very low, close to 1 meter square per gram. So that could be enhanced to 192 meters per gram when we are having a porous SiCO coating on nanocarbon. Now, in the same way, you can see the pore size distribution lies in the range of 3 to 4 or less than 5 nanometer. This was also confirmed by the SiCO coated nanocarbon hybrid, where you can see a difference in the nanocarbon and SiOC coating clearly from the TEM image. Now, when we have etch the sample, we expected to increase the surface area. It was shown correctly that when you're increasing the surface area up to 1400 meters square per gram, although depending on the pre-ceramic polymer, you can increase the surface area close to 2000 meters square per gram. And that could be very much useful for the electrical double layer capacitor for energy storage applications. So if you look into the pore size distribution of some those samples, it will be clearly seen that the pores lie in the nanopore range. So this two characteristics, one is the surface area, other is the pore size. These two things prompted us to go for its application in the energy storage application like ADLCs. So here we have tested the samples nanostructured SiCO for its application in energy storage, and we could observe we could get a very high value of 227 farad per gram. Although this was done on a lab scale, it has not been taken up to in the pilot scale level. But yeah, this results very much interesting, and this was published in two journals basically, ChemCom and Microporous and Mesoporous Material. So we got a very cyclic voltammetry studies where we don't have any contribution from the Faradic process, and that results in very low ESR, close to 1.5 ohm. In that case, we have achieved.
Dr. Abhishek, if you can conclude quickly.
Yeah, this is the position of my work, that we have developed porous bodies from this range, like from nanometer range to microns range. Like we have developed nanostructured SiCO where porosity is very, where the pore size lies in the range of 1 to 5 nanometer, and we have developed macroporous SiCO where the pore size lies close to 300 to 400 micron. So here I would like to acknowledge Professor Shantanu K. Behra from NIT Rourkela, who has been my mentor, my PhD guide, and he introduced me in the area of PDC. I would like to thank Dr. Ashish Agarwal for allowing me to utilize the synchrotron X-ray source. I would like to thank DST sir for the financial support that I got. And I would like to also thank for my research, former research scholars. Actually, when I was doing my PhD, at the same time I got a permanent position. So I had to migrate from my doctoral studies, and the juniors have, they have taken off, and they have used this materials for developing in the lithium-ion battery, supercapacitor, and other application. So with this, I thank you and wish you a very happy Holi.
Thank you very much, Dr. Abhishek, for the excellent presentation and also the graded porosity, how that can be produced. We'll take a couple of quick questions because actually we are running 5 minutes late.
Okay.
Any questions for Dr. Abhishek?
Yes. Abhishek, nice presentation. And I just want to ask you a question. When you are etching with HF,
yes, sir.
You told that the silicon will be removed from the system. But basically it will remove the whole Si and O also, no? Like Si, O, it goes...
depending on the etchant concentration and time. Basically when silicon leaves the system, it creates some strain on the material, and it makes the carbon to get aligned along the graphitic layers. So we will be seeing all this TEM image you may have seen, that we are having a graphitic layers of carbon around the nanocarbon. So we get oxide derived carbon there.
Okay, and how do you see that if you're the temperature at which you have pyrolyzed or ceramic converted is 1200, I understand.
In the case of nanostructured SiCO, we have done it 1000 degrees centigrade.
1000 degrees. So
yeah.
we have selected that particular temperature?
Yeah, we have optimized that one, and we have to see that we get a better porosity or better surface area. We are getting at 1000 degrees centigrade.
Based on the porosity generation and surface area.
Yeah.
Okay, thank you.
Thank you.
Okay, we'll conclude here because we are running behind time. I think further questions you can take it during the lunch break networking.
Thank you very much, Dr. Abhishek. I now request Shamra sir to give the memento to Abhishek sir.
I now invite Mr. Maggot Becky to deliver the keynote lecture He is the chair of Advanced Ceramic Materials, Institute of Material Science and Technologies, Technical University of Berlin, Germany. He would be delivering his lecture on metal-containing ceramic nanocomposites synthesized from metal acetates and polysilicene for energy storage and catalytic applications. Over to you, Mr. Magid.
Thank you. Hi. Okay. Okay, so good morning. We're still morning. Thank you for introduction, and it's a pleasure for me to be here today to present our project focused in the synthesis of metal-containing BDCs for energy storage application, catalytic application. So polymer-derived ceramics is one of the focused research topic in our group in Berlin, Advanced Ceramic Materials. In addition to this, we have a lot of interesting research topics, but I'm not going to present them today, as most of other people did, because Professor Gollo is going to make also presentation within this workshop, and I think I expect he's going to do this presentation better by him, not me. Okay, so why metal-containing BDCs? You know, metal has some fascinating functional properties which can be used for many applications. However, I don't know if the pointer doesn't work, it seems. Okay. Okay, so they suffer from low thermal, chemical, or mechanical stability. In contrast to this, like polymer-derived ceramics have this good, excellent mechanical or chemical or thermal stability. So this means embedding this metal inside a matrix from BDC, we could overcome this kind of stability problems for the metals. For example, previous work showed that metal-containing BDC can use for heterogeneous catalysis such as copper or palladium silicon carbonitride, or they can be used for anode for lithium-ion batteries such as tin silicon oxycarbide, or if this metal have some magnetic properties such as iron or nickel or copper, they can use for magnetic application or microwave absorber, and if they show some antifungal or antibacterial properties, they can use for medical application. Okay, so in this project, we tried to develop a simple way to synthesize this material. Look into the literature, we found 3 common methods can be used for the synthesis of this metal-containing BDCs. The most common one and simple one is to mix different metal or metal oxide salts or material directly to polymers, and then after the pyrolysis, we end with the metal containing the BDC. The problem with this approach that most of the metal or metal oxide are inorganic and they are not insoluble in organic solvent, which we need to process. So I have a problem with the sound here. So you hear me like this? So is this better? Okay. Okay, however, this material are insoluble in organic solvent, which you need to process this pre-ceramic polymer. This means the final product usually suffer from heterogeneous distribution of this metal or metal oxide in the final product of BDCs due to this aggregation of the metal particle or metal oxide particle. The second approach is to pyrolyze organometallic polymer. However, the number of organometallic polymer are very limited. This means we can not do this for each metal or metal oxide material. In one hand, second hand, also we can't control the stoichiometry here because we can't increase the amount of metal content in the material or microstructure. And the last approach, which is very well common in case to overcome all this problem, is to do modification of pre-ceramic polymer with some metal salts. Following by the pyrolysis, we could obtain this metal-containing BDCs. Similar of this salt material, such as iron or cobalt carbonyl material, or metal alkoxide, or metal acetyl acetonate material. However, this kind of salts are not available for each element. Also, there is some approaches. We will do some synthetic metal complex material, and after preparing this material, they could react them with the pre-ceramic polymer. However, this also time-consuming process. So in our project, we try to check the availability of reacting commercially available metal acetate with this pre-ceramic polymer to, since this salts material is available for each element, so we can produce a lot of metal-containing PDCs if we are successfully could do this kind of approach. We selected for our study polysilicon polymer, namely Durazan 1800, which has a, as you can see here, it's a problem to see. You can see they have some functional group like silane group or amino group or vinyl group, function group, vinyl group, which could be interesting to react this metal acetate through this functional group. And since this polysilicon material are sensitive for oxidation or atmospheric conditions, we try to do this assembly first here, as you see in the left side in the glove box. By doing or preparing two different solutions of the metal acetate and the polymer in tetrahydrofuran solvents. And we take this assembly from the glove box after we prepare this two solutions without starting the mixing the two materials together. And then we take this assembly and we connect with the Schlenk line to do the synthesis under argon atmosphere to protect the system from oxygen and atmosphere condition. And this reaction, usually it's kind of exothermic reaction, so we don't need to use any temperature or heating the system, or we can do it at room temperature, or even sometimes we have to use ice baths to absorb all this releasing temperature. And you can see here in the flask here, this is an example of the nickel acetate material before we start mixing the pre-ceramic solution polymer, pre-ceramic polymer solutions with this material, and immediately after 5, 10 minutes or 1 hour here after the mixing the polymer with the metal acetate, we can see change in the color from green to black, which indicating that the formation of this single phase precursor, and the dark color here or the black color related to the formation of the metallic state of nickel. And we have tried this process, as you can see in the right side here, in addition to nickel acetate, more than 14 different metal acetate with different oxidation states, such as manganese, iron, copper, cobalt, zinc, and silver. And all, as you can see in the metal or obtained metal-containing precursor at the bottom here, that's the change in the color of all this metal acetate salts, indicating the successful reaction between this polysilicon polymer and the metal acetate. Worth noting also, we observed during this chemical reaction the ammonia and hydrogen release by detecting this by gas chromatography. So in the first step, we try to study the chemical structure of our metal-containing precursor. And as you can see, this is the FTIR spectra of this. Sorry, there is no light here, laser light for this. It does. Okay, okay, and now I see it. Sorry. Okay, so now I see it. Okay, so with looking here to the pure polymer and the spectra for metal-containing precursor here, we can see this NH group, the absorption band rate to the NH group or vinyl group. It has been remarkably decreased, or it furnished in some polymers, in some precursor here, compared with the pure polymer. And also we can see here or detect this carbonyl or absorption band related to the carbonyl group here, which indicates that this metal acetate material is attached to the polymer chain. And this chemical reaction most probably taking place in the course of this vinyl group or this CH group or NH group. We try to confirm this finding by doing solid NMR, and this is the carbon-13 NMR from the pure polymer and the nickel-containing precursor and palladium-containing precursor. And clearly also we can see that here the carbonyl group related to the acetate group is attached in the precursor, as we can see from the signal corresponding to this carbonyl group here. And also we see the signal related to the vinyl group. It's furnished in carbon-13 NMR spectra from the precursor material. So from here we can conclude that most probably this metal acetate react with the polysilicon polymer through this vinyl group or the SH group. But however, you know that this kind of polysilicon material does hydrosilylation reaction, which usually takes place at 100 degrees C by reacting the vinyl group and the SiH group or silan group. But however, in our case, as I mentioned before, we did this chemical reaction at room temperature or ice bath. This means the presence of our metal acetate could also catalyze this cross-linking process of dear than 1800 even at room temperature. Also, our XPS result, as we can see here, comparing the binding energy of different elements from p orbital or d orbital of all elements, we could find that all this binding energy correspond to the metallic state of this material. So from this XPS spectra, we can confirm that we are successfully reduce this metal cation in metal acetate during this chemical reaction, and we form metal in most of the precursor. In addition to this, also we observed higher oxidation state for manganese, iron, and zinc, which could be related to the presence of unreacted metal acetate in this precursor or during this process. Our TM characterization, as you can see also here, showing this nice distribution of this metal-containing precursor for nickel and palladium, and also from selected area diffraction pattern, we could confirm this is the metallic state of this element in this case. And we have a particle size, or this round particle size, about 3.5 nanometer or 3.6 nanometer, which is very nice for different, it will be very nice for different application, as I explain later. So here, based in this previous result, FTIR, NMR, XPS, and TM, we could confirm that we form a metal in our precursor before even we do the pyrolysis. And this can be explained, or this is the reaction mechanism explains the formation of metal. In the first step, this metal acetate will react or attack this silan group, and during this process will produce hydrogen atmosphere. As I mentioned, by gas chromatography, we detect this hydrogen atmosphere, and the metal will be reduced most probably by this hydrogen. And next step in the formation of this acetic acid as side product can be attack against this amino group or NH group in the polymer, and release ammonia, as I mentioned, also detected by gas chromatography, or it can also react with SiH again, and you release the hydrogen. Okay, so in the next step, we try to pyrolyze. After we successfully obtain this metal precursor, we try to do the pyrolysis because we need this for application. So we have to convert this pre-ceramic precursor to ceramic material, and we did this in 3 different temperature, pyrolysis temperature, in argon atmosphere, and we can see here at 1100 degrees C, this is the highest pyrolysis temperature we have used for this work. We see the ceramic yield for all this metal-containing precursor is higher than the pure polymer, which is about 66%. This means this metal acetate, when react with the polymer, we could increase the ceramic yield in one hand. In other hand, also, as I explained before, the metal acetate could catalyze this hydrosilylation reaction and increase the cross-linking degree of the polymer. And when we have the pyrolysis of this material at 700 degrees C, we can see that the metal is still stable for most of this metal-containing precursor. However, in some precursors, such as manganese oxide, we see only amorphous matrix of silicon carbide. We don't detect any metal. This means manganese most probably doesn't react during this process. But also, we found at this temperature for cobalt and palladium and nickel, also minor amount of nickel silicide is formed. With increasing the pyrolysis temperature to 1100 degrees C, we can see that the silicon oxycarbide matrix, amorphous matrix, start to be crystallized to silicon carbide or silicon oxynitride material. In addition to this, most of the metal start to react with the silicon segregated from this matrix and form metal silicide. Except for copper and zinc and silver, we still have a stable metal in this condition. Okay, after we successfully have this metal containing BDCs, silicon oxycarbonitride, we try to use this material for different application, and we selected this dry reforming of methane, which is very important catalytic reaction where we can get rid of this greenhouse gases, methane and carbon dioxide, and we form this syngas, hydrogen and carbon monoxide. However, this catalytic reaction, it is endothermic and take place at higher temperature above 500 degrees C, as we can see here from the energy, temperature, and Salby diagram. And if we do this reaction at lower temperatures than 700 degrees C, we have several side reactions here. As you can see, reaction 2, 3, 4, until 4 here leads to the formation of carbon. This kind of, in thermodynamic point of view, are favorable. And this carbon usually coating the surface of the active side of the catalyst and do the activation with time for the commercial catalyst. Or if we want to do this process at higher temperature, we will face centering of the catalytic active particles, and this centering of the particle also leads to the activation. So by embedding this material in silicon oxycarbide, we could prevent the aggregation or the contact between the particle, and we prevent the sintering process if we go to higher temperature. And before we do the catalytic test, of course, it's very important to check the surface area and porosity in the material. And we look in here for the sample pyrolyzed at 700 and 900 degrees C for nickel. There are micropores with high surface area. With increasing the pyrolysis temperature, we have non-porous here material with dropping the surface area remarkably. The same for palladium, but in case of the palladium, the non-porous material start to be formed even at 900 degrees C. And by testing this material as a catalyst for dry forming of methane, and here we plot the carbon dioxide conversion with time, which is very common to see how much carbon dioxide converted with time at 4 different temperatures. We can see that the catalytic activity increased with time here for nickel and the palladium catalyst here, and the best activity has been observed for nickel, the sample pyrolyzed at 900 degrees C, and for the palladium for the sample pyrolyzed at 700 degrees C. And this result is expected because these two materials having the highest surface area among all the samples. And it's very important also to understand the stability of the material. We do both characterization in the spent catalyst after drier forming of methane tests. And we found that from XPS that the carbon amount in the surface of the catalyst increased for all the catalysts. And we found the maximum increase or the highest increase in the carbon content in the surface for the sample showing the best activity for drier forming of methane for nickel and the palladium. This means the amount of carbon formed in the surface in our case is not related to the activation of the catalyst more than activating the catalyst or intermediate material to activate the catalyst. So this is known for many catalytic materials. This carbon nanotube can be formed in the catalyst, as you can see here in the right side. This is the material before the catalytic experiment, and this is after the catalytic experiment. And we can see this nice carbon nanotube formed. And it's known this kind of carbon nanotubes, they are active intermediate, which can be react with carbon dioxide and oxidize to form carbon monoxide during this catalytic reaction. So from this work or previous work, we could confirm that. Also, I forget to mention here, look into the particle size. We don't see too much centering in the particle size of our catalytic material. So from this work, we could conclude that embedding this nickel or palladium in the PDCs, we could improve their stability, and we don't see any long-term deactivation process during this catalytic reaction. The second part of application, we have used our material, as I mentioned before, tin can be very promising anode for lithium-ion battery. And looking here, this is the theoretical capacity calculated for tin compared with silicon oxycarbide matrix or graphite, which commercial anode material used, or other type of carbon. We have a much higher theoretical capacity in this case. However, during the alloying of tin with lithium and forming this lithium-rich alloy material, we have large volume expansion with about 260 volume, which leads to crack the tin particle during discharging process. So this is a problem here. Most of the tin material or tin electrode material suffer from the poor cycling stability for long time of charging discharging. And it's the same as for catalytic nickel and palladium. By embedding the tin in the matrix, we could also increase the stability of this material if we are able to hinder the formation of this high or lithium-rich tin alloy, so we can reduce the volume expansion in this case. So in this process, we did different concentration of tin to study the amount of tin influence in the cyclability of the material with using 40, 70, 150, 250, and this is the weight ratio of the metal acetate used in the synthesis. And looking from XRD, we can see that tin is stable in all the material after the pyrolysis at 1000 degrees C. And from TEM characterization here, we can see the spherical particle with about 14 nanometer, and with increasing the amount of tin acetate during the chemical reaction, we could see some agglomeration of the particle here, leading to increase in the particle size. And so I'm very close. So at the end, we also did some elemental analysis before do the battery testing, and we can see here the amount of tin is increased in the resulted BDCs with increasing the amount of tin acetate, which as expected. And looking here, the electronic conductivity of different electrode material with increasing the amount of tin, which has a metallic conductivity, we could increase the electronic conductivity of all these BDCs, which could be very good for battery testing. And here's the cyclability and rate capability of these different BDCs we synthesized with different amount of tin compared with silicon oxycarbonate material, which doesn't have any tin inside. And we did this battery testing at different C rate or different current density here, and we can see that the capacity decreasing with increasing the C rate, and this is expecting for such material. But when we decrease again the C rate, again we could recover the capacity. This means we have a good capacity retention. And all the tin containing material have a capacity higher than, or discharge capacity higher than the silicon carbonitride, and the capacity increase with the tin amount. And also we can see here we could test this material for more than 1,000 cycle, and the cyclability of this material looks very stable and very good. And also looking here, this is a microstructure of the material after 1,000 cycles, and we can see the particle is quite stable. There is no cracking or pulverization in the material. This means our BDC, we could stabilize this tin during charging, discharging, and the reason could be coming to the formation of lithium 7 to 10-2, which have less lithium than this structure here with 22 to 10, and this leads to only 195 volume expansion percent, compared with this one is much higher, which leads to this crack propagation in the particle. And also we did in situ XRD for this to confirm this alloy formation of lithium, which agree with the differential capacity measurement. So to conclude, we developed in this project simple route to synthesize metal-containing BDCs for several metals, and we tested some of them for catalytic applications such as nickel and palladium, showing good activity compared with the commercial available catalyst. And also we showed that tin silicon oxycarbide can be worked for as a node for lithium-ion batteries. And in Outlook, we tried to test some of this metal-containing BDC for gas sensing application or both lithium-ion battery for sodium or magnesium. And for the sample pyrolysis at high temperature where we have the metal silicide is formed, we are planning to test this for thermoelectric, as the metal silicide is already known as a good thermoelectric material. So this is, I would just acknowledge my PhD student in this project, June Wang, and this is our group in Berlin and different institutions which finance our research and our work. Thank you for your attention.
Thank you very much, Mr. Magid. Very excellent talk. So maybe we can take one question because we are running behind late. Yes.
On slide 10, you showed the ceramic yield. So if you make, so you have the Durazane 1800, and but how to say, if you compare what you put in, let's say what is not ceramic at the beginning, and if you compare with the ceramic yield, what would you have expected?
Yeah, so here we determine less ceramic yield. So if consider the amount of just single metal acetate and Durazane 1800 is a weight loss, we did this also analysis, and we found here we have a little bit of wait list of the as compared with the expected ceramic yield.
So we'll close here. Thank you, Mr. Magid. Those who have questions, they can use a lunch break to interact with Mr. Magid.
Thank you, sir. I request Shamra sir to to present the memento to Magid sir.
Thank you. So much. Thank you.
Thank you. We will now move to the last keynote lecture of this session by Mr. Ulrich Dagenhardt. He is the head research and development at QSIL in Germany. He'll be presenting his lecture on silicon non-oxide, silicon nitride and silicon carbide special qualities, recent developments and potential for electronics, analytics and green energy solutions. Over to you, Mr. Ulrich.
Oh, sorry.
Oh. No? So thank you very much for your kind introduction. First, I want to present my company. It is the QSIL group. QSIL is a quite strange word, even in Germany. It means Quarz Schmelze Ilmenau. So it contains in this abbreviation both the business we have and in the second the location Ilmenau in Germany. And fused quartz was the main business, but however, since 5 years, the company grew in a large scale because the business was quite successful and the shareholders are quite financially strong, and so they purchased some other mid-cap companies to diversify the business towards refractory metals, toward oxide ceramics, and also toward non-oxide ceramics. And so, in the center of Germany, a larger company group has grown, which is focused there, but which has also some other facilities in the Netherlands, in the UK, in China, and also some sales offices around the world. The revenue is about 200 million euro, and there are about 1,100 employees worldwide. So one of these companies, which was purchased some years ago, was the QSIL Ingenieurkeramik, formerly founded about 25 years ago as FCT Ingenieurkeramik. And for long years, it was managed and owned by Dr. Beroth, who grew up the company not only in size, but also in technology and ceramic competence. And about 4 years ago, he decided to retire, and 2 facilities with approximately 140 employees found a new home within the QSIL group. And our main businesses are monolithic ceramics, silicon nitride, silicon carbide, also some composite materials, and they are manufactured for very different technologies and industries. And as you can see here, also the shape and the size is varying very strong. So we have the machinery and the equipment to manufacturing very large and very complex shaped components, as well as very small and precise parts. And in small production numbers, but also in larger series. And we always consider the needs of our customers regarding the size, geometry, also the material. And one topic is also that we are able to develop the material towards special property profiles. So this is our background. Let's have a look on the production process. We are highly vertically integrated, so we are purchasing the ceramic powders, the organics, and then we are mixing, milling, and granulating then on our own chemistry. Afterwards, these powders are pressed to compacts by cold or isostatic pressing or by uniaxial pressing, and then they can be machined afterwards to enable near net shape manufacturing. Sintering is done, gas pressure sintering, vacuum sintering, and for high performance qualities, also hot isostatic post-compaction can be done at temperatures at up to 2000 degrees C and 2000 bar nitrogen or argon atmosphere. And to get the desired shape, the desired surface quality and tolerances the customer needs, also hard machining can be done. So today I want to present you the additional benefit which is created by the development of some special silicon nitride and silicon carbide grades for different applications, electronics, analytics, green energy solutions. And here on this slide you can see while other competitors provide 1, 2, or 3 different silicon nitride qualities, you can see here we have already 10 different qualities, and each of these quality is designed towards a specific property level. Besides the standard gas pressure sinter quality, we have a HIP material with increased performance, mechanical performance, and reliability. We have high purity material with use of high purity ceramic powders and also with reduced additive content. We have a material with increased corrosion resistance, material with increased thermal conductivity, a special material for high temperature application and higher creep resistance. Then electrical modified components. You know, silicon nitride is isolating, but you can also shift this by adding of some titanium nitride, for example, towards electrical conductivity. And last but not least, there are also some composite materials with zirconia and alumina to get some special composites for CTE, mismatch adjustment, and also to get a more wear-resistant material. And for the 3 application examples I will bring here, I will present here, these quality are of increasing interest. So first I will start with electronics. Electronics is quite important, but most people don't know how important ceramics are for the manufacturing of electronic components and devices. And this already starts with the manufacturing of the chemicals which are needed, chlorosilanes, and some balls, some ball valves, some tubes, some chemical reactors are made out of silicon nitride. Also afterwards, for the manufacturing and processing of high purity silicon powders, air classifier wheels and pelletizer rolls are used. And you see quite complex shapes which can be realized regarding the demand of our customers, but also the special grade SNPU allows and gives additional benefit by minimizing cross-contamination effect because we have an art-similar material. And this story of success for the ceramics continues. The highly pure silicon powder is melted, it is crystallized to ingots, and then it is thawed to a wire saw to wafers. And these wafers has to be handled, and again with reducing cross-contamination effect. And also for this, some wafer chucks, wafer trays, vacuum plates are used, which are made out of silicon nitride ceramics. You can see here also the shape is quite individual. Some surface structures can be realized, but also such long cross holes for the integration of some sensors, vacuum adapters, and so on. And in the last years, also a special silicon nitride quality gets more and more in focus for this application, because the handling has to be done at a certain temperature level, and to achieve this level as fast and as precise as possible, the customers need a material which has a higher electrical thermal conductivity. Here on this slide you can see the basic value for the silicon nitride is at about 25 watt per meter Kelvin. But when we use our silicon nitride special quality as an TC, we can reach up of 3 times higher values at room temperatures. So the story goes further on. When the electric structuring is done, also the electric circuits and chips has to be tested to separate the bad ones from the good ones. And this has to be done by some probe cards, typically in the so-called MEMS design. This means you have a ceramic plate and you have several thousands of electric contacts. And this can only be realized by some very thin and very planar silicon nitride plates, diameters up to 350 millimeters. And you see the thickness is in the several hundred micron area. So this is a challenge, because afterwards the customer has to structure it by some laser, and then some gold contacts are put on it, up to 50,000 contacts for the larger ones. And so high requirements on the material. It has to have a high purity, it has to be defect-free, and it is also important to fulfill the requirements on the planarity, on the surface quality. Matte lapping is some topic which is rising, not only flat grinding. And yes, and also in this case, silicon nitride special qualities get more and more importance. The reason is quite easy. The people need a material which has a similar CTE value than the silicon materials, or even if you go further on, the silicon carbide materials for the semiconductor. And the silicon nitride has a very low CTE curve. You can see it here in this range. And our special grade SNZO allows the adjustment of the CTE to a higher level towards the highly pure silicon. There are also some SNEC materials, but this is the material with the titanium nitride. It is electrical conductive. It is not suitable. It is for some other purpose suitable, of course. But here you can see by this composite material, this CTE can be shifted. But now let's switch to another application. Some analysis techniques, XRF and ICP analysis, allow the analysis of some iron ore, some mineral sands, some cements, and also some ceramics or geological samples. And for the sample preparation, it is necessary to melt these powders within a lithium or borate or sodium borate glass. This is done in so-called borate fusion machines. And the challenge here is that this process is done at temperatures up to 1,200 degrees C and also under quite corrosive atmosphere. So it is done in platinum crucibles with some platinum tools, and also the holders has to withstand high temperatures. So in the first years, these holders and cradles were made out of Hastelloy. However, in the last years, they were replaced. The manufacturer of these machines demanded for a material which is more corrosion resistant to have a higher lifetime of these holders. And so they discovered that especially the special grade SNPU provides temperature resistance, creep resistance, as well as the corrosion resistance which is needed. So all the larger manufacturers of these machines changed to the SNPU. However, in the last 2 or 3 years, there were some new developments to increase the cycling of these machines to allow up to 5 cycles per hour. This is not only challenging regarding thermal shock, but it is no problem for the SNPU. Another problem occurs. The cradle is not only tilted here, but it has to be removed completely out of the furnace and has to be put on a special rack. And when this is done at 1,200 degrees C, then you have really a problem because some passivating silicon oxide layer is forming on the surface of the SNPU. It is self-passivating, but when it at this high temperature, it causes some sticking effects between the holder and the rack. And so the customer came to us, oh, we have a problem, have you a solution? Then we thought a little bit about it, and then I recognized, oh, probably this can be solved by a specific polymeric derived coating. So I contacted my colleague Günther from the University of Bayreuth and said, is it possible to make an anti-sticking coating for the SNPU? And here you can see some results. We used an anti-sticking ceramic powder in combination with a pre-ceramic polymer and made a coating on the surface of the SNPU. And after some initial trials, you see some samples above, then we also made test coatings on such a holder. This was successful, but however, there are some challenges. The customer has to secure that this coating will be in place also after thousands of cycles. And so, of course, we have to secure that it can resist high temperature and chemical conditions. No weakening effects should occur, and also there should be a strong bonding between the substrate and the layer, and it should also withstand the thermal cycling, thermal shock, of course. Another example for some combination and some additional value by combination of a special silicon nitride grade and a polymer ceramic derived coating are efficient gas turbines for turbochargers. Most of you know that if the temperature in gas turbines is increased, also the efficiency increases, and so it is a dream for the gas turbine guys to substitute nickel-based superalloys by some ceramics to increase also operation temperatures. However, this is challenging. We have to develop a high temperature material with improved temperature and creep resistance, and then also the hot gas corrosion effects the problem with them has to be solved. And this can only be done by a special EPC coating. Here you can see some first results from some hot gas corrosion test. The mass loss is reduced with some EPC coating system. And you see that also it is not so easy to develop it. You need some bond code, you need some top code. This was done at the University of Bayreuth. So an example for this combination, special materials together with high performance silicon nitride. And so I will skip this, and I hope that it was possible for me to show you the possibility to modify silicon nitride, silicon carbide ceramics toward a special property profile. This will be more and more important for many applications and customers. And in some cases, you even need some functional coatings on the surface of the ceramics. This is done by, for example, by PDC ceramics. It creates a challenge because it needs a good communication between the customer, the ceramic manufacturer, and the institute or the coating specialist. But I hope I have shown the potential. Thank you very much.
Thank you very much, Ulrich. We'll take a couple of questions before we break for lunch. Yes.
So very nice presentation. I want to know, you who saw that SNEC, which is a conductive coating, right?
Electrically conductive?
Yes?
No.
It's not electric?
Not electrically conductive.
Okay. So
No.
all are electrical
But
insulator?
They are actually all electrically insulating.
Okay.
But of course, you can also think about electrical conductive coatings.
Okay.
Also, this could be a new topic, I say.
Okay. Yeah, thank you. And I have one more question. These coatings are used for can be used as a bridging materials to join between two
To join
metals?
the
Yes.
ceramics together.
Yes.
Yes, we made also some experiments with this, but it is not actual possible to do this in production scale. But
Okay.
yes, we are also working on this topic. In sometimes in combination with pre-ceramic polymers, in some situations, but in some cases also without.
Okay. Thank you.
You're welcome.
Thank you very much. One more question, please.
Yeah, thank you very much.
It works. The thermal expansion coefficient. It is here. It is a little bit lower than the standard qualities because we have here some lower additive content, and so it is shifted even lower towards the minimum level you can achieve with the silicon nitride. You're welcome.
Thank you very much, Ulrich. That was a great presentation. Thanks.
Thank you, sir. I once again request Shamrao sir to present the memento to Ulrich sir.
Thank you very much. Thank you.
I now request Ravi Kumar sir to present memento to Shamrao sir.
Now we have a small ceremony on the occasion of International Women's Day. So I would like to hand over session to Ravi Kumar sir.
Apart from ceramics and celebrating Holi, we suddenly thought that we should also celebrate the Women's Day. So this has not been announced in the program. We thought this should be a surprise. So therefore, it's not actually in the program. So I welcome all the women scientists who have come to the department and to the institute as a part of this workshop. In particular, we have requested Ms. Shubha Kumar, who is a Distinguished Alumnus Award winner from the institute. She's an alumnus of our department. We have asked her to come here amidst her busy schedule to felicitate the women scientists. I would like to just give a brief introduction to Ms. Shubha Kumar, who is here. Ms. Shubha Kumar is the Managing Director of Notation Synchrochrones Private Limited in Chennai. As I said, she is a graduate from our department. She graduated with a BTech degree in Metallurgical Engineering from our department. Subsequently, she went to pursue her master's degree in Material Science from MIT in the US. And she also obtained her MBA from Stanford University. And then she returned back to India. She was, of course, working for Applied Materials for some time. She returned back to India and she has been leading this company, Notation Synchrochrones. She's a respected leader in the auto industry. And she has won several awards from the industries. And in particular, I would like to mention that Ms. Shubha is recognized amongst the top 50 women in science, technology, engineering, and mathematics by the Confederation of Indian Industry. So I would like to welcome Ms. Shubha Kumar on stage. I would like to call upon a few scientists. Of course, there are a lot of women who have contributed to science and technology, and there are other women as well. But in particular, we would like to invite those who are participating in this workshop. So let me call upon Professor Kavita Arunachalam. She is a professor in engineering design, and she's an amazing scientist. She has several patents to her credit. She is very humble, though, but if you look at her CV, you will see that she's an amazing scientist and a technologist with several patents to her credit. I would like to invite Professor Kavita Arunachalam on stage. Professor Kavita, please come here. Kavita, right? Kavita, stay back. Can I invite Dr. Caroline Sitzman? Dr. Caroline Sitzman comes from the Faculty of Engineering, Chair of Ceramic Materials, Academic Counselor. She is the Deputy Group Leader of Working Group Composite Ceramics at the University of Bayreuth in Germany. May I now invite Dr. Michaela Wilhelm. She is a Senior Scientist, Group Leader, Polymer Derived Ceramics at the University of Bremen, Germany. May I now invite Dr. Manjusha Bhattabyal. She is a Senior Scientist working for the Center for Automotive Energy Materials at the International Advanced Research Center for Powder Metallurgy and New Materials. It's, for people who do not know, ARCI is an autonomous R&D center, comes under the Department of Science and Technology. It's located in the research park. May I also invite Dr. Abha Bharti. Abha Bharti is a co-founder and advisor for the Saratattva Innotech Private Limited. She obtained her doctorate degree from the Vikram Sarabhai Space Center, and she is leading this startup, Dr. Abha Bharti. May I now invite Dr. Tisita Das. She is working for the Harishchandra Research Institute in Allahabad. She is a physicist by education and training. So she is working for the Harishchandra Research Institute at Allahabad. May I now invite Ms. Melanie Wynn. She is working at the University of Limoges in France. working with Samuel Bernard, if I'm right. I also call two students who have been working day and night to make this conference, who have done a remarkable job. Neeraja Moharana, she is pursuing her doctoral thesis in the department jointly with me and as well as Professor Hari Kumar. I think many of them have not slept, I think, who have been. So may I now call Reshma Kupili. She is also pursuing her doctoral thesis in my department as well as jointly with Professor Kavita in engineering design. So I think big applause to these scientists. They have been doing amazing. Thank you so much. I would like to invite Dr. Günther Motz to give this gift to Ms. Shubha Kumar. Thank you. To her. We keep exchanging gifts. Yeah. Ms. Shubha is very busy and it's March, it's not so easy, but she agreed when I requested her to come here for a short time. So I would like to request her to say a few words and then, yeah, please.
So good afternoon, everyone. I'm really privileged to be here amongst top ceramic engineering scientists from around the world. I believe we have people from Germany, France, Japan, USA, and of course, India. And we have faculty members, we have scientists from government research labs, from industry, as well as from startups. So this is really a very good confluence of getting global talent in a specific field. And I thank Professor Ravi Kumar for having me here. Thank you so much. For me personally, material science is a fascinating field. And I think there is a lot of innovation that's happening today. And whether it's in EV or quantum computing, semiconductors, whatever it is, new materials play a big role in where we are headed. And in fact, in our business, so I run a manufacturing company. And we've made material science as a differentiator for how we play. And we operate in automotive, aerospace, and in renewable energy space. So, and I saw some 3 pillars in your chart. I don't know if that's all you're talking about, but maybe about other stuff as well. But I will talk about these areas. And as we all know, I think you know ceramics are a very crucial component for a wide range of industries. From in the automotive, for example, from fuel cells to engine components. They have very unique properties, and you know, they've been in use for a long time, reducing friction and so on. But this is just the beginning, right? I mean, in aerospace, you have ceramic material, matrix composites, and you create lighter, stronger, more heat-resistant alloys. We just saw about how they are used in impellers with thermal barrier coatings and so on. So we're only scratching the surface, even with all the level of ceramic adoption in the industry. And as we transition to sustainable, low-carbon energy sources, ceramics are going to play a much larger role in this world. So cutting-edge ceramic solutions, I see, will potentially revolutionize the way we think about energy, transportation, as well as aerospace. So but there is still a lot of work to be done, and you know, as ceramic scientists, you have the opportunity to shape the future of these industries and make a real difference to the world. You're pushing boundaries on where ceramics can be used, and we hope you can create more sustainable solutions and make the world a much better place for us to be in. I hope to meet all of you over lunch. and interact with you. It will be my pleasure to learn from all of you. Thank you so much.
Thank you, Ms. Shubha Kumar. I think now we can have lunch. Yeah, the lunch is on the other side.
One small announcement. So we will be starting our next session at 2 p.m. So I request everyone to be here by 11:55 as we will start on time. Again, the people who are not, who did not bring or do not have the food coupon for lunch can collect from registration desk. And I request everyone to bring food coupons for dinner today. Yeah, thank you. told him already. निकाला होगा ना इसका लैपटॉप है हाँ तो इसमें लगा हुआ है So welcome back everyone. We are starting our next session. Hope you had a great lunch. So I would like to call Mr. Ranjit Devasia to chair the session.
So good afternoon all of you. The theme of, well, I am Ranjit Devasia and I am from the Indian Space Research Organization. I will be chairing this session. And the theme of the session is precursor-derived ceramics for thermostructural applications. We have 4 speakers for this session. Every speaker will be given 20 minutes for their presentation, followed by 5 minutes for discussion. I'll be giving a bell at 20 minutes. I request all speakers to stick to the allotted time schedule. Now, the first keynote lecture will be by Dr. Uday Kumar, Senior Principal Scientist, Material Science Division, CSIR National Laboratories, Bangalore, India. I request Dr. Uday to come on stage. Now, Dr. Uday has 25 years R&D experience. He has more than 50 publications, 5 patents, and many technologies to his credit. He is a CVI CVD expert. I vouch to that. And he has won numerous prestigious awards for his contribution in the field of CVI CVD. And Dr. Uday will speak on high performance continuous fiber reinforced ceramic matrix composites for strategic applications. Over to you, Dr. Uday.
Yeah. Thank you, Chairman. So very good afternoon to one and all here. In fact, it is very tough to stay after such a nice lunch. So happy to see the many audience. So at the outset, I would like to thank Professor Ravi Kumar and Dr. Gunter Modes for giving me an opportunity to be a part of this this PDCITT program, and I'm sure I'm really happy to note that this team has worked very professionally. And I want to stress one thing, that this abstract book has been done so nicely. My congratulations to the team. So a lot of, I think, basically their creativity and their color scheme and other things, which all possible because of the freedom framework given by Professor Ravi Kurama, I guess. So I'll just move with this note. I would like to move on to my topic. So basically I'll be talking on this, the high performance continuous fiber reinforced ceramic mattress composite for strategic applications. So these CFCCs are very important. So this fiber can be a carbon fiber, or it can be a silicon carbide, or even some kind of a UHTC fiber. But in general, the classification is the CFTC. So I am Dr. Uday Kumar from Council of Scientific and Industrial Research Organization, which is headquarters in Delhi. And there are 38 laboratories spread all over the country. I am from a place called Bangalore, city called Bangalore, is a garden city of India, and also is a Silicon Valley. So I am from the lab, which is National Aerospace Laboratory. Our main mandate is to design, develop and fabricate the civilian aircraft. And as you all know, this developing the aircraft is interdisciplinary in nature. So in turn, we have a lot of technically activated divisions like material science division, propulsion division, and so on and so forth. So I am from material science divisions. Now the outline will be just a brief introduction about my continuous fiber reinforced ceramic mattress composite, and how they are very crucial in terms of applications in strategic areas, and especially two workhorse material I'll be discussing. One is the Igstc, that is silicon carbide fiber reinforced silicon carbide mattress composite, and the other one is the carbon fiber reinforced silicon carbide mattress composite, and how these materials are developed, and characterization and some key results will be discussed, and some of the products which we have developed at our lab will be also discussed, and I would like to summarize at the end. So we all know that ceramics, we have been hearing from a morning, that is a very interesting class of material with a lot of interesting attributes like high hardness, high chemical inertness, high wear resistance, high refractoriness, and so on and so forth. But they do suffer from drawbacks, basically the brittle failure, catastrophic failure, and poor impact and thermal shock resistance. And because of this, they do suffer from what is it called a poor reliability in properties. So though they have got a very interesting attributes, but in some very high-end applications, we cannot use these materials, especially silicon carbide, being a very good non-oxide ceramics with very interesting properties. But because of this poor reliability, we are not able to use it. But to take that material and bring the secondary phase in terms of in the form of a fiber or a whisker or in the particle, and control the interface between the reinforcement and the matrix which is surrounding the reinforcement, tune that microstructure, and then you see the wonder that is called a CFCC. So whereas you see this red line, which is the tensile strength of the silicon carbide, monolithic silicon carbide, which is CVD derived. But the fiber, silicon carbide fiber or a carbon fiber, if you take, the strength is very high, but the ductility is low. But if you combine this fiber and this matrix and tailor the interfacial bond strength between the fiber and matrix, not too weak, not too strong, around 10 to 15 MPa strength, then you end up with a composite which has got a wonderful behavior, a strength reasonably very high compared to 100 MPa. Now we have got something like a 230 MPa, and the displacement, your damage tolerance is increased. So the damage tolerance increases because of this, the energy dissipating events which you have introduced because of the embedding the reinforcement, matrix cracking, then crack bridging, then you have a fiber pull out, then you have an interfacial debonding and fiber movement and so on and so forth. Because of that, the fracture is delayed, whereas earlier as a monolithic ceramics, they have only the maximum by which it can absorb is only the fracture, ultimate fracture of the bond, whereas here, so before that happens, you have lot of other phenomena to absorb. So that is why this material is more damage tolerant and useful for the actual applications. So if you take these two workhorse material, like carbon fiber is embedded in SiC matrix, silicon carbide is embedded in SiC matrix, especially derived from a CVI process. It has got application in almost all strategic sectors. For example, you take a defense, hypersonic applications, where it can be used in the wing leading edge, nose tip, and thrust vector, and these components are basically by using this CSIC and SIC components. And also it is finding application in space. In fact, ISRO is looking very closely at this system, especially this reusable launch vehicle. There are many areas they are using this materials in their missions. And of course the energy, fission reactor as well as the fusion reactor. We have a fission category high temperature nuclear fission reactor where they want to use the CSIC for flow channel, the high temperature reactor. And also the fusion category, the 6C components are being used as a flow channel insert for their fusion, especially the ITER project. So International Thermonuclear Experimental Reactor, which is the multi nations are involved, where this material is being spoken as very crucial for their success. And also the aerospace, basically the gas turbine engine, we use these materials in the variable orifice nozzle system, especially in the exit side of the hot end aero engine applications. These components are being used. Apart from that, I will also be touching upon some brake disc, the CSIC brake disc, which is the better compared to the carbon-carbon composite in terms of friction performance and stable properties with respect to the So the process which we use to manufacture these is basically a CVI. So we know that chemical vapor infiltration process is the process where we bring the reactants in the form of gas and allow them to react with each other on the substrate, which is nothing but our preform. And if you keep doing these reactions over a period, what will happen, this porosity will be filled with that matrix. So thereby we finally end up with the CMCs. The basic principle is the chemical, this is all very basic. So this is the preform. The preform can be made by using any fiber, carbon fiber or a silicon carbide fiber. And this preform can be a simple layup, just a fabric layup, or it can be a braided structure, or it can be a noobed structure like 3-dimensional or 3.5D or 4.5D. And this is heated to the reaction temperature in the reactor, and the gaseous reactants are allowed to diffuse. This is a via chemical diffusion, and the reaction takes place. So in order to improve the uniformity, we also rotate the whole component during the reaction. So that actually changes the boundary layer so that the uniformity in densification is improved. So if you see the densification rate, so initially the slope will be very high. As you all know that the fibers, if I say the carbon fiber, not a single tau, it is basically, it has got a 3000 fiber in it. So after interface coating, what happens is that it has got, sorry. I'm sorry, this is not. So initially the slope is high because the surface area is more, so that the deposition rate is very high. As this basically when you start the infiltration, initially the surface area is more, so that it is happening in the interfiber densification. Once that is over, then the interbundle, so inter-tau space is more, and that will start filling it up. So that will keep surface area is coming down, so that it is going, the slope will come down, and after some time it won't increase any further. So that is the maximum density one can obtain from this process. So imagine this, this is the fiber architecture. So green, say warp direction fiber. I am just taken just for the understanding purpose. The green is say warp x direction fiber, and red is the weft, that is a y direction fiber. So if you do this reaction, originally start like a CVD only, but if you keep doing it, so what happens, bundle also will be eventually closed, and thereby finally I get the densified product. So the process worksheet is going like this. First the preform has to be made. As I told, the preform can be a simple fabric layup, or it can be a braided structure, or it can be a noobed structure. and go for the, and since it is a compliant mask, you have to have a tool to retain that shape. So it is loaded into the tools, and go for the interface coating, because the interface coating is basically applied to change the interfacial bond strength, that thereby I don't get the very high interfacial bond strength or very low. Both are not useful for me. If it is very low, it is not mechanically strong. If it is very strong, that is not a damage tolerant material. So I need to have a modified interfacial bond strength. For that purpose, I am having the interface coating. This interface coating, either by cracking methane in this temperature and the pressure regime, I get the pyrolytic carbon, and boron nitrate interface is obtained by boron trichloride and ammonia, and in this pressure regime and temperature regime. So depending on the requirement, I will apply this interface coating, but this interface coating is less than 1 micron, few hundredth of nanometer. After that, I go for the matrix infiltration, which is I am using the precursor methyl trichlorosilane, CH3SiCl3, so which crack at that temperature and form a silicon carbide in situ, and if I keep doing it, eventually it will have a densified preform, that is a dense composite. Since it is an isothermal CVI, generally it has a tendency to close the premature closure of the surface pores, so that is called a canning. So in order to clear that, what I do this, intentionally I will break this process, that is stop the process, take the product out and remove the skin, and again I will put it for infiltration, thereby I increase the density. So this is a set, we have a gas manifold system, we have a gas mixing chamber, and this is the reactor. In this, this is a reactor where I get the this one, and then it comes to the scrubber, so that I can normalize and send it the safe gases outside. So this is the reactor facility which we have. Is basically the 1400 degrees centigrade, pressure capability up to 1 to 300 millibar, and I can do a silicon nitrate, boron nitrate, pyrolytic carbon, and the silicon carbide. And the reactor size is something like almost 850 mm diameter and 1 meter in height. So that is the size component I can handle. So basically this already explained. This system is carbon fiber is reinforced in the silicon carbide matrix. The procedure wise more or less same, and only the difference is that in the is a bidirectionally woven cloth laid one over the other, and I am introducing the stitching by stitching Z direction fiber to improve the ILSS and other properties. So because of that, it is called 2.5D. So 2.5 directional, that is a nomenclature. So this material in special, because this is called a self-healing matrix composite. So I have a fiber to protect that and have a tailored interfacial bond strength. I have a multi-layer interface. You can see this pyrolytic carbon followed by silicon carbide, and the whole pair is repeated by 4 times. That means there are 8 layers. So if any oxygen comes at high temperature, before attacking the fiber, it has to attack these 8 layers. That is a level 1 protection. And the level 2 protection is that instead of simple SiC alone, I introduce a boron in it. So what happens at high temperature in the oxidizing environment, the boron will react and it forms a B2O3, and SiC passive oxidation will give silicon dioxide, SiO2, and these two react and it forms borosilicate glass. And if at all any surface defects is there over a period of time, if it is a conducive passive oxidation, it will seal the automatically heal the surface pores. So thereby it is a level 2 protection. Level 3rd protection is I give the seal coating of silicon carbide as well as the boron bearing silicon carbide, and because of this CSIC we call it as a robust CMC. So with this approach we have made the laminate of something like 250 mm by 250 mm by 6 mm, 4 to 6 mm thickness. So this is our scheme. We generate the test coupons in terms of mechanical, thermal, all these things by water jet cutting. And so we characterize this. So as I told, these are all the layers, different multi-layer interface, SiC pyrolytic carbon, and we have SiBC, and the face is also identified like the silicon beta silicon carbide. Tensile behavior, you can see it's a very nice curve. where you have up to some region, it is a linear elastic, it follows the Oak's law, and beyond then there is a non-linearity starts and it goes, so there is a delayed fracture. And all the tested samples, you can see that the fracture happened in the center and it is not the cleavage fracture, which you can witness by from this the fracture micrograph, a lot of fiber pull out, so matrix cracking, so many things as operative, this fracture phenomena, and thereby it is a damage tolerant behavior has come. So this is with respect to the thermal exposure. We have exposed at 1250 degrees centigrade and 1350 degrees centigrade for more than 100 hours, and we tested it. So in one case, in the 1250 case, the reduction in strength is very low, so that means it has protected my self-healing, and boron, this one multi-layer interface has given the proper protection for that. And of course 1350 we saw some drastic this one. So we saw that there is some kind of oxidation has happened. So this has to be, what we have done is we have improved the thickness of the seal coating, and that we have improved this also, 1350 also it has served. And this is the thermal cycling. So we have cycled between the something like 1250 degrees centigrade and 80 in a few minutes time, and it is 100 cycles it has withstood, and almost retained 80 to 85% of original strength, residual strength, and the fracture surface also tells me that it is not the cleavage fracture, it has retained that behavior. And flexural strength is very good. You have got up to 350, 360. This is a very good value for this class of CMC. And you can see the fracture micrograph. You can see almost all sorts of fracture processes like matrix cracking, fiber bridging, and fiber pull out. Everything is there. And this is the set of properties, because I have not gone into detail. So you can see density, porosity, elongation, and especially the ILS is quite high compared to this. And fracture toughness is very good, is 29 MPa root M, that is what is required for this class of CMCs. And it has been compared with the SNECMA value. And this is for 2.5D. And this is for 3D composites. So this also in par with literature values. And one classic case I will explain. This is the brake disc. As I told you, the CSIC brake disc has got an advantage compared to the metal. Metal density is very high, and they have the poor temperature capability, and it starts like a powdery stuff it will come when the brake is applied. Carbon-carbon is good, but the carbon-carbon problem is they do suffer from what is called early morning disease. That means when the moisture is there in the environment, the friction coefficient is very low. So, and temperature if it is high, it will oxidize. Because when you replace this carbon matrix by silicon carbide, you have a stable friction performance, and also since matrix is silicon carbide, it has got a very high temperature capability. So because of that, this material is superior brake disc material as told by this consortium made by almost all the aircraft manufacturers. So if that's this one, yeah, I'll take 2 more minutes. So this is our Saurus aircraft. Currently we are using this metallic brakes, and this one is the rotor and the other one is the stator. Rotor will be rotating as per this the wheel speed of our aircraft, and the rotor will be there when you apply the brake by this one, and it has to absorb the whole energy. So we have developed CSIC, and we have done this. This is a composite we have made by using the T300 fiber and CVI process. And in addition to this, as a hybrid process also, we have taken the liquid silicon infiltration process, where first we made the carbon-carbon by using the phenolic resin as a precursor. So carbon fiber, PIP process we will use, and then we get the carbon-carbon. And the carbon-carbon is eventually treated to a very high temperature in the molten silicon. So molten silicon will infiltrate and then react with carbon, and it forms a silicon carbide. So that we have got almost all the properties, brake disc relevant properties in terms of thermal, mechanical and friction, tribological properties. They are in par. So after seeing that, what we have done is we have gone for this is a microstructure of that. So you have the fiber and interface, and this is the the disk, a few sets of disk we have made, and this has undergone what is it called the dynamometer test, because originally first the coupon level, then we have to go to the disk on disk level, which is replicating your flight requirements. That is done by the dynamometer. So the dynamometer test results showed that it has performed very well with respect to the mechanical and also thermal, but the only problem is the friction coefficient is quite low compared to the coupon level value. Because of that, what happens, it takes longer time to stop this one. So the research is going on. This is the dynamometer which we have used at RCA Hyderabad, and these are results. So the friction coefficient is quite stable after this one. That is very interesting. But the only thing is we need something like a 0.3 to 0.4 as a coefficient of friction, but we are in roughly around 0.2. So this improvement is going on now by modifying the matrix. And last but few slides, this is actually the silicon carbide composite with the pyrolytic carbon interface and boron nitride interface without any treatment. And this is a boron nitride interface between the silicon carbide and silicon carbide, but it is treated with the intermediate heat treatment, and this is a subsequent heat treatment. With this we saw that very interesting result. So the tensile strength is very good, and fiber pull out and other things are there. This is for the pyrolytic carbon interface SiC composite, and this is very interesting, which has been published in European Ceramic Society. So the intermediate heat treatment given to this SiC composite, that boron nitride has gone there, whatever the unreacted stuff is there, it has been removed, and that has improved the interfacial bond strength between the fiber and the matrix. So thereby the strength is increased. So these are very interesting findings. And this is the properties of this Igstc composite. And these are all the some products which we have developed at our lab. This is the hypersonic components, basically the 3D CSIC, where the carbon, this is used as a nose tip for hypersonic test demonstrator vehicle. And this is the Igstc 2D. And this one is the flap, convergent flap slave for the gas turbine engine application. This is undergoing some testing at the field level test. And this is for the wing leading edge, and this one is the nuclear reactor applications. So to summarize this, basically we have the capability to take up this this kind of material development, and it is a very challenging, because starting from machining to the realization of the product. And this CSIC with the self-healing matrix and multi-layer interface is given the very interesting results, which we are continuing it. And also the Igstc composite also has got, of course, getting the silicon carbide fiber is a challenging. Now with respect to the brake disc, we have reached almost going to the flight trials, but we need to improve this coefficient of friction. So in this regard, in fact, I am open to some collaboration in this particular area, brake disc, high performance brake disc, CSIC brake disc. So if any German friends are there, I'm really happy to discuss, and we'll take it forward. Thank you very much for your attention.
Thank you, Dr. Uday, for that very informative lecture. I think the session is open for discussion. We'll have time for one question probably.
How did you test the brake materials? So you said a dynamometer. Can you say something about the dynamometer?
Yes. So this dynamometer, basically the disc on disc type. What we have done is we have arrived at certain test conditions based on the flight design, that brake disc design, especially in terms of the deflection radius, and then the takeoff speed, 195 km/h, the takeoff speed, and what is the linear speed of this one, and with respect to the mass, total kinetic energy has to be absorbed by this brake. So based on that, we will decide what is that total energy which has to be dissipated by one pair of phase. So that worked out to be something like the dynamometer rotor has to be rotated with something like a 1690 RPM, and when I apply the brake, it should dissipate 1.15 megajoule of energy, and temperature should not go beyond 400 or 500 degrees centigrade. That is a requirement, because if it is going very high, the tire will be heated, and tire is nitrogen filled and it will burst. So we don't want the temperature to go very high, and the wheel has to stop, that is the rotor has to stop to 0 speed in 15 seconds. Right now our material is taking 32 seconds. So that we saw that the basic problem is to improve the coefficient of friction, and also what we saw that the surface roughness, that whatever the face contact should be improved. So that is where we are looking for, and also we are trying to change the fiber architecture and the base material. So instead of silicon carbide alone, we would like to include some 10-15% of ferroelectric carbon, so that my base material has got a better friction resistant material.
So thank you, Uday. Can we have one quick question?
Yeah, thank you for the talk. My question is like, when you are using that precursor for the CVI process, you are expecting a stoichiometric silicon carbide deposition.
Yes, yes.
But during your optimization trials or sometime, have you ever noticed that the non-stoichiometric, like carbon rich or silicon rich, or what might be the reason for that?
See, basically, I have not gone into detail. You must see that the flow rate ratio, that mass flow rate ratio, molar flow rate ratio between with respect to your hydrogen to MTS, it should be more than 10, less than 16. If it is very high hydrogen compared to MTS, or very low hydrogen compared to this, both the conditions will lead to have free carbon in one side and one side free hydrogen, free silicon. Both are not good for your mechanical application. So you have to see that your molar flow rate ratio should be around 12 to 16, so that your silicon carbide what you are getting is stoichiometric, which will be 100% beta silicon carbide.
Thank you.
Yeah.
Okay, thank you, Uday.
Yeah.
It was a wonderful lecture.
Now I request Mr. Ranjit Devasya to hand over the memento to Mr. Uday Kumar.
The next speaker is Dr. Carolyn Sitzman. She is the Deputy Head of Working Group Ceramic Matrix Composites, Chair of Ceramic Materials Engineering, University of Bayreuth, Germany. May I request Dr. Carolyn to be on stage? And Dr. Carolyn will be speaking on the influence of hexamethylene tetramine on the cross-linking and pyrolysis of Novolac resins applied as carbon precursors for CMC. Over to you, Carolyn.
Okay, thank you very much for the nice introduction. I'm pleased to be here, so thanks Gabi and Günther for the invitation. I will talk about results of my colleague Felix Wich, and it's regarding carbon precursors and especially on the influence of hexa on the cross-linking and the pyrolysis of Novolac resins. So please have a look on the new presentation. It's just impressed, but we have already the DOI, so please click or save the DOI by QR code. So first of all, I will show you the applications for phenolic resin-based materials, and I will explain the types of phenolic resins and the hardening mechanisms which will occur. Also, I will talk about the pyrolysis reactions, which are known yet. So I will present you the material and the methods we are using, and of course the results and discussion of the results. I will close my talk with a summary and a short outlook. So the phenolic resins are a really old material. They were invented more than 100 years ago by Leo Bakeland, and they are polymers which are based on polycondensation reaction between phenol derivatives and aldehydes. So where can you find them? So you can find them as carbon precursors for CMCs if you use the liquid silicon infiltration process, or you can use them as foundry sands. Also, we can find them in the medium density fiberboards, or like in the talk before, we can also use them for brake pads as binding materials. A very wide range of use they have in circuit boards and electronic insulators. So as you can imagine, every application has different requirements on the resin regarding the viscosity, the reactivity, and so on. So our thought is it would be really fine to have adjustable resin systems which can be which can be adjusted to the processes you need. So which is the state of the art. We have the basic reaction of the phenol the phenol groups reacts with the formaldehyde, and they are building methylene bridges, and water is released. So we have to determine the account and the conditions of the reaction. It can be in the acid or in alkaline conditions, and it's important to know the ratio between the formaldehyde and the phenol groups to determine the cross-linking mechanisms and reactions. So for Novolac resins, we use the acid conditions, and for resol resins, we use alkaline reaction. Also, it's important for Novolac resins to have formaldehyde to phenol ratio of smaller than 1, and it's important to have an additional hardener for a full cross-linking. So the most commonly hardener is hexamethyl 18 tetramine. It's so-called hexa, and I will show you which effect the hexa has, or if the hexa can be adjusted for a perfect curing and the polymer properties. It's in the literature, it's known that the pyrolysis reaction consists of 3 main temperature ranges. Smaller than 300 degrees C, there are post-condensation reaction and a release of water and free phenols and other non-reacted monomer substances. Between 300 and 700 degrees C, there is a release of phenols and bisphenols and trisphenols, and above 700 degrees C, you have a release of short-chain hydrocarbons and so on. So in the literature, mostly it's only reported about the whole pyrolysis process, and there's rarely reported about simultaneously thermal gravimetry, FTIR, and gas chromatography results. So my colleague used 2 different types of resins. We have on the one side the bakelite 6109, which is provided by Bakelite Synthetics, and it has a hexa content which is mixed by Bakelite Synthetics. So we are here fixed to only 4 different hexa contents. But we have used the other resin. It's called Bakelite 0235, and there we was able to define very different hexa contents to study the influence of a specific hexa content. The resin and hexa mixtures were compounded in a tumble mixer for 20 minutes, and we used 5 ceramic milling balls to get a homogeneous mixture. For the TG measurements, we have cured all resins in a convection oven at 170 degrees C for 1 hour. So which methods we have used the Anton Parr rheolometer for the rheological measurements, and it's a plate-plate geometry, is 25 millimeters. And we have used a measurement gap of 1 millimeter, but it changes when the resin starts to foam. So we used the normal force control of 0 Newton. We heat it up to 100 degrees C, and then we measure until 170 degrees C with 2 Kelvin per minute in the oscillation mode. For thermogravimetry and evolved gas analysis, we are using a system from NATCH. So we have basically here TG DSC with a coupled FTIR directly on the heating chamber, and it's coupled with a gas chromatograph and a mass spectrometer. So when we have a look on the viscosity or the complex viscosity in special, we can see that there is a curing 225 to 125 to 150 degrees C, and you can see there is a strong temperature dependency on the hexa content. So we have on the one side, we have an increasing of the complexity with an increasing hexa amount, and you can see here some buckling effects. This occurs due to the foaming, and the temperature of the foaming is decreased with higher hexa contents. So we can say that the reactivity and the viscosity rises with increasing hexa contents. On the thermogravimetry measurements, we can see that the carbon residue and the residual mass is also depending on the hexa content. Without hexa, we have 35% residual mass at 1000 degrees C, and above 13% hexa, we will receive 57 to 58% residual mass. So you can see there's a kind of plateau above 13% hexa content, and I can say that the results are similar for the other bakelite system. If we show about the residual mass about the hexa content, so we can see that there is an exponential dependency on both values, and you can use the Arrhenius equation to model the resulting residual mass depending on the hexa content. So there is an interconnection between the curing reaction and the polymer structure. If you show on the FTIR results, we can see 4 main pyrolysis steps, which are there visible. So we have the 100 degrees C for the absorbed substances like water or CO2 or ammonia. We have a temperature step until 270 degrees C, where our post-curing reaction occurs, and we have 2 main steps at 550 degrees C. So, but for those steps, the FTIR didn't show any results which substances will release. So we have to use here the gas chromatography and the mass spectrometer. So we can see on the DTG curve that at the temperature of 400 and 550 degrees C, there's a dependency on the hexa content. So for low hexa contents, we have here the minima in the reaction. So the main pyrolysis occurs at 400 degrees C, and above 9% hexa, we have the main pyrolysis steps at 550 degrees C. To see what happens is we can use the evolved gas analysis, and there you can see that on 400 and 550 degrees C, there is the same result like in the thermogravimetry. So we see that the results and the elements are the same, but we have the same reaction, but on different polymer chain architectures. So we can adjust by the hexa content the resulting polymer architecture, which changes the pyrolysis reaction. So to sum up my talk is we have seen that there are resin systems with adjustable viscosity and reactivity behavior with, I have shown you that the complex viscosity is connected to the hexa amount in a nonlinear way, and the foaming shifts from 152 degrees C with 3% hexa to 130 degrees C. The resin system has the adjustable carbon residue and the pyrolysis kinetic behavior. So we see that the maximum carbon residue is above about 58%, and this is obtained at hexa contents up 13% and higher. So the charge yield can be modeled using an exponential function, and the main pyrolysis steps differ between 400 and 550 degrees C. I have only also shown that there are 4 different pyrolysis steps in the temperature, and we will prove the applicability of these resin systems for other applications, like for foundry sands or refractories. So we will investigate the influence of the heating rate on the pyrolysis reaction, and we will determine the thermal, physical, and morphological properties of the charge. So I want to thank you for your attention, and I want to thank the German Research Foundation, DFG, for the funding, and especially Bakelite Synthetics for providing us the resins. So if you have questions, please feel free. Thank you.
Thank you, Dr. Carolyn, for the wonderful lecture. Now the session is open for discussion.
Thank you very much. It's a very nice presentation. This curing you are doing in what kind? Is the pressure is above atmospheric or?
It's atmospheric pressure, yes.
So do you come across foaming as a issue or?
Normally not, because we have adjusted the temperature curve to it, and in combination with the fibers, it's we have a warm pressing process, so we can reduce the foaming.
This your hexa content, is there any? Is it having any role on yield, carbon yield?
The hexa content?
Yeah.
Yes, it's high influence on the hexa on the.
So maximum you got up to?
58% for the matrix.
Thank
so
you.
it's.
Yeah, thank you very much for a nice presentation, dissecting the Novolak hexamine system. Just one maybe comments from Dr. Uday Kumar, what he told. No? Maybe that hexamine content can be 9 to 12%, usually will maintain.
Yes.
Because beyond that it will have the very high hardness, so you defeat the purpose of the application.
Sorry?
Defeat the purpose of the application. Because if it is hard, it will be brittle.
Yes.
So it may not be useful that what you are intending to use this material.
Yeah, this was the thought on the own mixtures to see the effect of the hexa content.
True.
And then we will, in the next step, we are looking for other applications than CMCs. So then we know we can adjust the properties.
And what is the solvent you are using to dissolve hexamine? Any idea you can share?
We are mixing in the powder directly in the tubular mixer.
No, just suggestion from you. Do you think that any solvent can be used to mix hexamine within the bakelite system?
We don't need a solvent.
Any solvent you can use to mix hexamine?
You can isopropyl or something like this use, but for our process we are using the warm pressing method, so we can use the powder form.
Okay, thank you.
We have one more question, yes.
Okay, thank you for this interesting presentation. So I worked with this Hexa before, and I know this problem with ammonia release, and I just curious, how did you do a special procedure during the pyrolysis to get off of this ammonia and not to be danger someone in the lab?
Yeah, we have a air cleaning and the post-curing process on the oven. So, yes.
If we do not have any more questions, I would like to thank Dr. Carolyn for this wonderful presentation.
I'd like to ask, I'd like to request Mr. Ranjit to hand over the memento to Ms. Carol.
The next keynote lecture will be by Dr. Gunter Moos, who is the head of work group Polymer Derived Ceramics, Chair of Ceramic Materials Engineering, University of Bayern, Germany. Dr. Moos is the author of over 130 peer-reviewed publications and patents. His current research work is mainly focused on novel metal-containing silicon carbonitride precursors, fibers, coatings, and catalytic active ceramics, to name a few. So today Dr. Moos will speak on ceramic fibers, functional coatings, and catalytically active ceramics based on tailored commercial oligosiloxanes. Over to you, Dr. Moos.
Yeah, namaste. It's again me. And now I would like to give an overview about some scientific activities at our institute. And therefore, I would like to talk about the development of ceramic fibers, functional coatings, and catalytically active ceramics based on tailored commercial oligosiloxanes. We received from Merck company, and Jürgen Mertes from Merck is also here, and therefore that makes me also very happy. And this work was in collaboration with Professor Redkempe from the inorganic chemistry from the University of Bayreuth. But at first, I would like to show you where is Bayreuth. Here you can see Europe, and in the middle of Europe is Germany. And here you can see the states of Germany, and in the southeast, one of the biggest states is Bavaria. And the capital of Bavaria is Munich, very popular because of the biggest beer fest worldwide. And about 250 kilometers in the north of Munich is Bayreuth. And Bayreuth has a population of about 75,000 people and 5 breweries, which is very important for the Germans. And Bayreuth itself is a very attractive small city. Here you can see the campus. Professor Schaffner already showed the campus. It's a very nice place in the middle where the students can have a lot of fun and events. And then we have the Wagner Opera House. It's world famous, and it was founded by the composer Wagner about 150 years ago. And then we have a lot of castles around Bayreuth and parks. It's really nice to see. And we have also a very old opera house, a Baroque opera house. It's about 300 years old, and this is under the UNESCO heritage. And here you can see the composer Richard Wagner itself, and he's the godfather of opera in Bayreuth. And he founded the oldest opera festival worldwide in Bayreuth. And therefore, Bayreuth is very famous, especially in Japan and in the United States. And, and here's the campus. Again, we have about 30,500 students, 7 faculties, and the university is very young, was founded in 1975. So now I come to the scientific program. You can see the typical chain you have to follow when you would like to develop ceramic by using precursors. You start with the synthesis of a polymer, which was done by Merck already, and also commercialized in one of the biggest facilities worldwide for the processing of, or for the production of siloxanes is here in India. And therefore, IIT is the right place to have a PDC workshop. And the number of available precursors, especially in the case of siloxanes, is limited. And therefore, our task is to use these commercially available siloxanes to modify this for special applications. And this is what we are doing, and we are using we take the precursor polymer from Merck, and we make some chemical modifications. And then we, by this chemical modification, a cross-linking step is followed. This cross-linking step is crucial to have a ceramic material at the end. That means we need a 3-dimensional network which can be transferred during temperature step between 500 and 1400 degrees C to an amorphous ceramic. And then when you go to higher temperatures, this amorphous ceramic can also crystallize. Here you can see some examples of commercially available siloxanes. This is called PHPS. This is the Durazane 1800. This is Durazane 1033, all commercially available. And at first I would like to show you that we can make from these liquids, all these precursors are liquids, how we can make from these liquids a solid and meltable polysiloxane. Here we started with, for example, the HDT 1033, was called in the past MS33, and Durazane 1800, the old name is HDT 1800, it's a liquid. And then we looked for a suitable catalyst to make a cross-linking which leads to a meltable polymer, not to a completely cross-linked polymer which is untunable and unmeltable. Our aim was to get a meltable and tunable polymer. And we checked the literature, and a very famous scientist from France, Professor Couriou, found out that with a fluoride catalyst, it is possible to activate the bond between silicon and hydrogen, and this leads to a reaction of the SiH with the NH bond of the siloxanes under the loss of hydrogen, and the formation of a new bond between silicon and nitrogen. And this reaction is relatively slow. That means you can terminate the reaction at a special point, and this is possible with a calcium salt. When we add the inhibitor, the calcium salt, then we can stop the reaction. That the reaction works as proposed can you see here by using FTIR spectroscopy. In this case, we used at first gas chromatography, and we found out that the evolved gas is only hydrogen. And here you can see the FTIR spectrum from the precursor we used as received, and the cross-linked or the polymerized precursor. And here you can see that the signal for the SiH bond is strongly decreased. That means the reaction works as proposed. And by varying the amount of the catalyst, the reaction time, it is possible to tailor the properties of the precursor. You can tailor the molecular weight, the weakening point, the solubility, and so on. This is only an example. And such a precursor we used for the melt spinning process to develop ceramic fibers, to develop ceramic SiCN fibers, which is one of the topics at our chair. Then we compared these polymer with another polymer from our chair, which has no functional groups like SiH or vinyl groups, with the the groups with the polymers MS33S and HTTS. These are the polymerized precursors. The MS33S has NH and SiH as functional groups, and HTTS has NH, SiH, and Si vinyl. And then, because we developed these solids for the processing of ceramic fibers via melt spinning, we investigated the rheology of the precursors. And as you can see, the viscosity decreases as expected with temperature. But in the case of HTTS, after a temperature of 170 degrees, we have an increase in viscosity. This comes from the polymerization of the vinyl groups. Therefore, we can use all the precursors up to a temperature of 150 degrees C without changing the properties also after a longer time during the melt spinning process. Another positive effect was that we can increase the ceramic yield by this polymerization step. Especially dramatically is it by using the Durazane 1033, which has usually a very low ceramic yield of only 30% weight percent. And by using the fluorine catalyst, we have a ceramic yield of more than 70%. Then I come to the next example, the insertion of functional groups to functionalize the precursor and, for example, to produce functional coatings. At first, I would like to show you some commercial applications of siloxanes. Here you can see the reflectors made from aluminum are coated by a siloxane to protect the aluminum from scratch, that the solar power can heat up these pipes. Otherwise, if you have sand, then the sand scratches the alumina sheets, and this leads to a decrease in the efficiency. Another example is that PET is coated by PHBS as a diffusion barrier against water and oxygen. And then a very prominent example is to use siloxanes as an anti-gravity coating for trains. It is called Tutobrom, also used in India. And Jürgen Mertes will give more examples about this. And the most important application is to use the siloxanes as a dielectrics in electronic devices. And this is the best solution ever. I think the business is more than 500 million euro. Is it right, or is it higher? Or it's around that. Yeah, and the advantage is it's a liquid, and here you have the electronic structures, and the gap between the electronic structures is only or less than 10 nanometers. And only this siloxane can fill these very thin volumes between the electronic structures, and leads after occurring to silica, which protects these structures from electric currency. And here is an advertisement in Germany to use the anti-gravity coatings on the high-speed trains in Germany, that people which have not a good behavior should not do this, and we have the coating and can remove the color very easily. I would like to show you some examples from the United States. There's a company called NIC Industries, and they coated exhaust pipe systems with siloxanes. And then I would like to show you an example which cannot be transferred to India or to Germany. They like weapons in the United States, you know this, and there in every state of the United States you have the option to color your weapon as you want, and also for such applications siloxanes are used. But we used the siloxanes for other applications to generate a hydrophobic coating. And the problem of hydrophobic coating, mostly based on fluorine, is that the adhesion to the substrate is very bad. But we know that the siloxanes have an excellent adhesion because the most of the substrates have an OH group. And the siloxane react with OH groups, and this leads to a chemical bond between the substrate and the coating. And therefore, our idea was to use a fluorine-containing material, like a fluorine alcohol, and to combine it with a siloxane, which should lead to a fluorinated polysiloxane, and we can use for the protective coatings. You can see the strategy, the metallic substrate, the coating, it's very well bonded to the substrate because of the xylosane, and then we have the fluorine atoms at the surface. Yeah, we used this fluorinated alcohol, and also Mr. Coriou from France found out that you can use a silane, activate the SiH group, and then this silane can react with an alcohol, for example, by the formation of a silicon-oxygen organic group bond. And then we combined this reaction with the reaction I showed before for the polymerization of a xylosane. And then we have simultaneous reaction between the alcohol, this fluorinated alcohol, and the polymerization of the xylosane via the SiH and NH group. And at the end, we had this fluorinated polyxylosane. And as you can see here, the contact angle of the xylosane is already very high, 97 degrees to water. But by adding 5 weight% of the alcohol or 10 or 20 weight% of the alcohol, it will further increase up to 110 degrees C to water. And beside this, also the corrosion protection was improved in hydrochloric acid, but also in potassium hydroxide. Then I come to another topic. This is the reaction with organic polymers, which lead to hybrid polymers. And the question was, is there a ceramic or is there a fiber material between the properties of the very expensive ceramic fibers and carbon fibers? And to improve the oxidation stability of carbon fibers, one way is to apply a coating on the fibers, but it is better when this property is already in situ of the fiber. And therefore, it is, we try to combine PAN, polyacrylonitrile, with the xylosanes, because polyacrylonitrile is very well known as the precursor for the processing of carbon fibers. And with xylosanes, we can produce ceramic fibers. And therefore, we combined both polymers. And here you can see that carbon fibers have an excellent high tensile strength. Ceramic fibers also. The E modulus is also comparable. But there are big difference in the maximum operating temperature. Carbon fibers less than 400 degrees C. Ceramic fibers higher than 1200 degrees C. And also the price is very different. Carbon fibers have a relatively low price, starting at 20 euros, and ceramic fibers starting at 2,000 euros. Therefore, the other aim was also to reduce the cost of the recycling fibers. And therefore, we reacted acrylonitrile with xylosanes, and then we pyrolyzed the hybrid polymer, and we investigated the oxidation stability at up to 1,000 degrees C in air. And as you can see, this is the carbon material burnt completely. And the higher the amount of the xylosane, the better is the oxidation stability. And already when we added only 40 weight% of xylosane to PAN, we have a dramatically reduced oxidation instability. And then we tried to produce ceramic fibers or carbon with ceramic fibers with this polymer. As you can see here, the fiber material looks very nice, but the diameter is very high. And this comes from the dry spinning process, which led only to very thick fibers. But we oxidized such a fiber in air at 800 degrees C. And as you can see, in contrast to carbon fibers, the fiber is intact. Another PhD student from my group, Jakob Denk, will give a presentation how we solved the problem to reduce the fiber diameter. And this is the strategy to reduce the oxidation instability. After pyrolysis, we found that the material is composed of turbostratic carbon, ordered graphite-like regions, and amorphous silicon nitride. And when the oxidation starts, the oxidation front reaches the silicon nitride particles, which are nano-sized, And this leads at the end to a front which is composed of silica and silicon nitride and protects the material from further oxidation. Now I come to the last topic of my presentation. This is the reaction with metal complexes, which was in collaboration with Professor Red Kemper at our university. And we followed this strategy. We used the xylazane, and then we added metal complexes. And all these metals, red marked in this table here, we already included in our xylazanes. And these complexes react with the backbone of the xylazane, leading to a metal-modified polyxylazane. And then we added DCP as an initiator to enhance the cross-linking of the material, and polyethylene as a sacrificial filler to form pores during pyrolysis. And then we pressed the body from this mixture. We cured this at temperatures up to 300 degrees C and pyrolyzed it up to 1100 degrees C. And at the end, we had a metal-modified ceramic material. And there was a very nice work between Samuel Bernard and Professor Kumar here at IIT. And they found a way to generate hydrogen from sodium boron hydride. But it is always a problem to make this controlled. And therefore, they looked for a catalyst. And one of the most prominent catalysts for this case is a platinum catalyst. And for this, they developed a platinum-containing silicon carbide or silicon carbon nitride. And with such a catalyst, it was possible to tailor the formation of the hydrogen. To produce such a catalyst, there are two options. The one is the self-assembly by using, for example, OH-terminated polyethylene reacted with HDT 1800, Durosane 1800 to form a hybrid polymer. And then you can form a body from this. After pyrolysis, you have a porous system which you can use for such catalytic reactions. Another option is to use a carbon template to infiltrate the carbon template with the metal-modified polyxylazane and then burn out the carbon, which leads to a porous system composed of the metal-modified SiCN ceramic. The next step was the generation of hydrogen is a very interesting topic, but how can we storage the hydrogen? That's always a big problem. And therefore, my colleague, Professor Kemper, developed a bimetallic catalytic system composed of ruthenium and palladium, as you can see here. And then it is known that you can use ruthenium as a hydrogenation catalyst and polyethylene, palladium as a dehydrogenation catalyst. And he used this very simple chemical molecule. And as you can see, this bimetallic catalyst has a higher efficiency in comparison to the single catalyst, iridium, palladium on carbon, or palladium on silica. But this is not the end of the story, because this is a molecule which must be synthesized firstly. And he thought that we can use much more cheaper materials like lignin. And lignin has a lot of very interesting structures. And via hydrogenolysis, this leads to the decomposition of cellulose to cyclohexane 1.2 diol. And with an iridium catalyst and SiCN, this leads to octahydrophenazine. And by using this bimetallic catalyst, we can add the hydrogen and we can remove the hydrogen from this molecule. And at the end, we could also increase the weight % of hydrogen which can be stored by this system. Now, at the end of my presentation, I hope you could follow a little bit, was a little bit fast. And at last but not least, I would like my former PhD students, who are almost working in industry now, and I would also like the DFG and other institutions for funding the work. But last and not least, I thank you for your attention, and I'm open for questions.
Thank you, Dr. Morse. I think now the session is open for discussion. We can have a couple of questions.
Was too much.
If no one is having a question, I do have a question. See, you were talking about that modification of acrylonitrile with silicon carbonitride. So have you evaluated the mechanical properties of the resultant fibers?
Yeah. These fibers are too thick. And there is always the rule, the thinner a fiber, the higher the tensile strength.
Yeah.
Therefore, our aim was to reduce the diameter of the fiber. But via dry spinning, it was not possible. And therefore, now we are using electrospinning. And with electrospinning, it's very easy possible. And we produced via electrospinning non-wovens, but we also try to produce single fibers. But I will not talk too much about this because my PhD student will give a presentation about this topic.
Okay, fine. I will listen to that.
These fibers have also these excellent oxidation stability. We tested the oxidation stability also.
Fine. Thank you.
Just one small query. You have shown that beyond 1450 degrees is possible to, so you can pyrolyze the first pre-ceramic polymer when you are taking. You are pyrolyzing, then first you get the amorphous phase, right? And you mentioned that beyond 1450 it will be started crystalline. So is it possible for the applicable for silicon carbide also? Can you get the good crystalline ceramics, silicon carbide ceramics just beyond 1450, or you have to go for still higher temperature?
For the crystallization, silicon carbonitride is not a suitable material because the thermodynamic stability of the silicon-nitrogen bond ends at a temperature of about 1450 degrees C. That means before the material can crystallize, it decomposes and under the loss of nitrogen. And at the end, you have only silicon carbide. If your aim is to produce silicon carbide material, which is crystalline and porous, then the SiCl material is a suitable material, but not to make a dense material.
Any more questions? So I think thank you very much for this wonderful technical experience sharing with us.
Now I request Mr. Ranjit Devasia to hand over the memento to Mr. Kuntar.
Thank you so much. Thank you so much. Thank you.
The next speaker is Dr. Santanu Mandal, who is Senior General Manager and Head R&D Unit, CUMI Industrial Ceramics Division. So I invite Dr. Santanu on stage. Yeah. Now, Dr. Santanu is a winner of numerous prestigious awards for his contributions, and he has filed 27 patents. Dr. Santanu will speak on CUMI, ceramic and composite materials, a quest on futuristic mobility. Over to you, Dr. Santanu.
This one is the light? Okay. Okay. First of all, thank you very much, Professor Ravi Kumar, for inviting us in the learned gathering. Right? It is a wonderful experience for all of us. Secondly, I must confess that I am not from, I am from industry. I am not
my presentation will not be so much structured like Professor Gunter Modes regarding the experiment, observation, inference. Rather, what I will say, I will share my experience in what we do in QME, a generic overview of the futuristic mobility, as well as some product what we do in the towards futuristic mobility. And here with me, our colleague, from corporate technology, Dr. Shyam Rao, Mr. P.S. John is available. They are actually pioneer in establishing, Dr. Shyam Rao pioneer in establishing the metallized ceramic facility in India in our company. I think this is the only facility we have in India. And Mr. Jayan is pioneer in establishing the solvent process and also working on the graphene. My other colleague was there. With that, I'll just start my presentation. Sorry. Okay, sorry. Yeah, QME is part of the Murugappa group. We belong to the engineering segment of the business of $6.5 billion Murugappa group. We actually, the genesis of QME with the tripartite agreement from Carbon USA, Universal UK and Murugappa group long back in 1954. We have 4 different kind of business units: abrasives, ceramics, superrefractories, electromineral division. This is our management team. Our MD was present in the morning during the inauguration. Our chairman, Sri M. Murugappan, I think he's traveling now overseas. This is the QME associate company. I think we spread all over the world. That QME is existing for more than, I told, 75 years, $400 million business. We have large export. In fact, our division, our export is around 75%, more than 75%. We export to Germany, USA, Australia, all part of the world. We have the DSS certified, government certified R&D lab, practicing IMS and TPM. This is the product segment for us. We have many different kind of product segments: various ceramics, metallized ceramics, solid oxide fuel cell, ceramic for the solid oxide fuel cell. So for a diversified industry. So if you see our grade of alumina, we produce actually mainly 4 grades of product: alumina, silicon carbide, zirconia, titanate. In alumina, we have many grades starting from 90 to 99.8% alumina. Silicon carbide, reaction bonded silicon carbide, sintered silicon carbide, zirconia for wear, thermal application, titanate for especially for non-ferrous molten metal handling industry, which is on the key material having zero expansion coefficient. So this is the process, the forming process we have, right from usual pressing, isostatic pressing, injection molding, slip casting, tape casting, extrusion, etc. So we manufacture the product with the help of many process, and we supply the product to different industry for wear. For zirconia also we supply to many industries, different grade of zirconia. These are metallized ceramic segments, is one of our key product. We manufacture we are one of the largest manufacturer of vacuum circuit breaker, ceramic part of the vacuum circuit breaker, supplying all over the world, including ABB Germany, Eaton, Schneider, all company all over the world. And we also manufacture metallized devices based on 94, 97.5, 99.5% alumina formulation. Also in the small way, we do ceramic to metal sealing and metal to metal sealing, brazing process, etc. So this is the thermal. We supply non-ferrous, titanate for non-ferrous and zirconia for ferrous industry. Coming to future mobility now, say what is the future of mobility will be fueled by disruptive technology. Why are we telling so? What is the main concern now? Rising urbanization. right? So people are moving from more toward the urban area. So it creates the more population actually. So number of accidents is high. Then environmental concern. The carbon footprint reduction is one of the key mandate for India as for the entire world. And changing customer needs, customer need to have the more experience than using the goods. So that will create the lot of changes going forward in futuristic mobility. Then obviously technological evolution. We don't want to drive car, right? We now want maybe the autonomous vehicle. I think such type of vehicle is existing in Germany. They can take the track of the road and can drive autonomous and can put the brake. We can set that maybe 50 meter, 100 meter so. So I think a lot of new technology will be coming into picture, and mainly maybe driven by the smart materials, sensor, actuators. Many new things will be coming on going forward. So what we require safe and integrated mobility. We want a sustainable environment where the carbon footprint will be reduced, and obviously affordability and competitiveness, right? And it can be multimodal shared, multimodal autonomy, anything, right? So I think if you see the mobility evolution, right? It started by maybe 1786 by James Watt, and with a steam engine. After that, we need to wait for maybe another 90 years. 1876, then Nicholas Otto come up with the IC engine. And I think after that, not major changes as far as the major technology is concerned. Now actually coming to the automation, right? Maybe 2010 onwards, we are seeing more and more automated vehicle, etc. So road like that, rails, then air, I think is coming, balloons to the helicopter, jet plane. Now we are going towards the drones. Maybe drones, when you recall, it is becoming more infamous, different way. But I think it is one of the key technology for agriculture, spraying the maybe fertilizer. Then maybe carrying the material from one end to other end, or one village to other village, right? So it can provide the enormous opportunity for all of us, right? So what it actually means, the experience, energy, EV, etc., the key driver for the future mobility. So if you see that one, usually I think mentioned by our IIT Madras director also, that we are looking for the specific strength, right? We want a material having good specific strength. Maybe that is the strength per unit weight, or more specific elastic modulus, which can determine the structural ability of the material. So when you see that material which is at the higher side will be taking the major role going forward, definitely, right? Obviously maybe the lower end material will be going by the cost, but high end, wherever you need to use the higher end material, we need to go for the top material going forward. So what mobility look like in the future? Actually lightweight vehicles, which can have the more maybe the more efficiency, delivery drones, vehicle sharing system, hyperloop, flying taxis, autonomous vehicle. This will actually form the basis of future mobility, right? So why ceramic is important here? Ceramic is having a diversified property among all, because it is a lightweight, high specific strength, excellent high temperature properties. We have been hearing that.
The mic is out.
Hello. Hello.
Battery.
Battery. No problem. So why ceramic is important now? This one?
Hello.
So you can use this.
I think it's okay. Why ceramic is important now? Because of lightweight and high specific strength, excellent high temperature properties. You have been listening throughout the since morning. Capable of insulation thermally, electrically. Also, it can act as a superconductor. Ceramic is the only material can exhibit the properties, can have the electrical insulating, again can behave as superconductor. So excellent wear and corrosion behavior because of its hardness, inertness, etc. Environmentally safe. That is one of the key driver for ceramics because it is environmentally safe and can display high Weyl modulus. So maybe more than 25, so we can have the more reliability as we move forward. That's why bulk ceramic like maybe used for automotive application like spark plug to miniature functional components like package, etc. can be made with the ceramics. So going for the next one, so these are the different kind of ceramics it's possible to use for making safe, sustainable, as well as affordable. So if you see that one, this is our group company, TI, Chola, etc. I think they started already launching the e-vehicle for different application. So in QME, we are manufacturing CFRP sheet, carbon fiber reinforced plastic or FRP for drone application. And so if you see that one, we manufacture tape-cast ceramics product. Then we have the technology for metallization by screen printing process. Recently, we have acquired a technology from Indian Space Research Organization, where actually we can sputter metal onto ceramics. That is usually we got for chromium, copper, gold. Chromium is the interfacial layer, copper is the conducting layer, gold is the inert layer. That technology has been space qualified. So it is being used for the microwave communication. When you are the spacecraft, all the things for microwave communication, these are the things maybe is used for. Then if you are coming, landing to Chennai, you can see the colorful FRP sheet. It is not only the for visibility, but also having less interference with the signal. This is also manufactured by our company. This is that brake pad. We are talking about that. Usually the hard material like silicon carbide, silicon nitride, hexagonal bond nitride. This is a mixture is being used for the brake pad application, having high hardness, high toughness, as well as very good insulating behavior. Right? And we supply the best quality of the grain worldwide to many manufacturers. This is a protecting vehicle or protecting jacket. It is used for many security personnel, including police, paramilitary, etc. So we don't make jacket. We supply ceramic part to the jacket manufacturer, and this is being used for a protective vehicle for various conditions. So this is the grinding wheel we manufacture for the easy grinding, smooth grinding to develop a very good surface finish. Usually used for the aerospace application. The launching pad of Indian Space Organization is actually supplied by us, that we supply the refractory material which can resist the high temperature while actually projecting the rocket in the sky. So QME has become a trusted partner for this national pride. Then that high-speed train, we use the ceramic electrical system. Ceramic fuse body is the metallized ceramics. We apply the glass coating or glaze coating on the ceramic so that it can be impervious, no leakage current you can have. Then we apply the metallization coating, metallization padding, and develop the fuse, which can be used for the critical component for the vehicle. So this is the ceramic fastener, which is being used for the fastening of the high temperature insulating material, mainly for spacecraft, etc. And this is the graphene. These are various kind of graphene, nano graphene, polymer master batches, where the graphene disperses in the polymer and can apply it on the surface. So there are various technology available. Its main thing, as you know, thermoconductivity, anti-static, rolling resistance is good, air leakage, etc. So it is also being used for battery, where high capacity we are working on. It is under R&D stage, faster charging, lightweight, flexibility, a high temperature range is being used. This SOFC, SOEC, we have put a lot of effort for that, and we are supplying the structural material to the fuel cell manufacturer, and we are also working for functional ceramic part as well, where the electrolytes based on fully stabilized zirconia, zirconia can be doped with the various rare earth material. We are working towards that. Also, we are working to develop the entire fuel cell. One is for electrical generation, electricity generation. Other is for hydrogen production, right? So green hydrogen will be. We are working with IIT closely, and see that one if we can develop the SOE cell for the green hydrogen generation. And also that few of the projects we are working with IIT Madras very closely. One is the hot filament CVD process for applying diamond coating on to improve the wear resistance behavior of ceramics. Mainly useful for high wear, high corrosion, wherever you require thermally dissipation, because heat sink, such kind of application. Also, one of the thing that silicon carbide target generation, then by doping, the selective doping, we can make the P-type or N-type semiconductor, and finally we can make PN junction. One of the projects we work with the IIT. This is the team who actually given various input for making the presentation. Thank you very much. Any question? I'm open for that.
Thank you, Dr. Shantanu, for that very informative lecture. So the session is open for discussion.
Maybe no more questions.
Now I have a question regarding the ceramic fasteners. What is the material of that fastener?
Yeah, it is actually fully stabilized zirconia, which will have the very good properties at room temperature till the temperature it is being used for.
Can you give me some figures like the tensile strength of the fasteners? What is the size? M6, M8 or?
It is M10.
M10.
What is shown here M10, but it's possible to make anything. Not a problem.
Okay. And we can use it up to 2000?
No, 2000 not. It is oxide material, zirconia material, fully stabilized one. So should be possible to use up to 1200.
1200.
1400 degrees Celsius.
Any more questions? If there are no more questions, I think on behalf of the organizers.
I would request Dr. Ranjit Devasya to hand over the momentum to Dr. Shantanu Mandal.
I think with that, we come to the end of the session, precursor-derived ceramics for thermostructural applications. So we had 4 lectures, and I thank all the speakers who have kept the schedule. We are right on schedule, Ravi, I suppose. And thanks to the audience for the good interaction. Thank you very much.
I would request Professor Ravi Kumar to hand over memento to Dr. Ranjit Devasya. Now we are having a break here and we will go for a high tea. I request everyone to come back here by 4 or 5. We will start our next session at 4:10. Yes. Thank you. No, this one. No, if it is on also, no issue, no. Let it be on.
Welcome back, everyone. So let's start our next session now. And this is the last session of the day. And this will be chaired by Dr. Michaela Wilhelm. And I request ma'am to come on to the stage and carry forward the session. Thank you, ma'am.
Yeah, good afternoon, everybody. So I'm Michaela Wilhelm from the University of Bremen, and a pleasure for me to share now the last session of today. And our, or probably I should name the name of the session will be once again, Precursor-Derived Ceramics for Thermostructural Applications. And we will have two talks, one key lecture and one invited talk. And the first talk will be given by Emanuel Ionescu, and I would like to ask him to come to the stage. Emanuel Ionescu, he works or worked at the University of Darmstadt for a long period and recently changed to another institute. This is now, and he's there, the deputy director and the head of the department Digitalization of Resources of the Fraunhofer Research Institute of Material Recycling and Resource Strategies. And now he will talk about his new area of research, and we are now looking forward to your presentation, Emanuel.
Thank you indeed, Michaela. Yes, thank you, Michaela, indeed for your kind presentation, and I'm very happy to be with you today. I would first like to thank to Ravi, Kumar, and Günther Motz, my good colleagues and friends, for inviting me here to join this excellent workshop. And I will briefly discuss with you. It's not very technical talk, but I will rather try to briefly talk to you about the concept of using compositional disorder as an enabler for recycling and circular economy purposes. And before doing that, I'll just briefly introduce the Fraunhofer Gesellschaft, which most of you might know. This is, I think, one of the largest research institutions worldwide, I think the largest in Europe, having around 30 employees. In total, there are around 76 institutes and research institutions, and they have a total budget of around 3 billion euros. And you see the institutes are spread all over Germany. And I will discuss today about our work at Fraunhofer IWKS. This is located here. We have 2 sites in Alzenau and Hanau. I will just show you on the next slide some activities we have at these sites. Frankfurt is here. You might know Frankfurt Airport, so we are very close to. And for those of you, because you have seen the title, that I still have affiliation with Darmstadt, and I am very happy to host, since longer time, master students from Professor Ravi Kumar in Darmstadt. Darmstadt is located also very near, so we have here a triangle of locations where we are doing our research. Maybe just a brief introduction of Fraunhofer IWKS, which focuses on materials recycling, circular economy concepts. And as I mentioned, we have two sites, one in Hesse, in the Hesse Bundesland, and then we have one in Bavaria, and we have seen one of the organizers represent the state of Bavaria with the University of Bayreuth. In Alzenau, we have two departments working on bioeconomics, trying to extract valuable components from biogenic waste streams, food waste and other waste streams, and doing additionally modification of those valuable components, trying to bring them as functional parts into novel products. And then we have a department which is called Digitalization of Resources, which I'm heading by myself, which does a lot of activities related to process and life cycle assessment, which meanwhile it's quite important and has a lot of relevance for various purposes. And we are trying also, for instance, to automatize processes such as sorting and separating processes. And in our site in Hanau, so by the way, these two sites are just 8 kilometers apart, so they're quite close to each other. In Hanau, we have two more departments, one related to developing circular economy concepts for energy materials such as batteries, solid oxide fuel cells, photovoltaics, and so on. And one department dealing with the development of novel concepts for the circular economy of magnetic materials, recycling of spent hard magnets, and so on. So, and I brought another slide related to our general strategy and philosophy at Fraunhofer IWKS. So this is the ultimate aim to provide a world without generating waste anymore, but these material compositions which you call waste should be considered as an additional resources for valuable materials. So we develop also materials for the circular economy, and we try to define sustainability as an additional intrinsic property of a material. So when we try to develop a material, we do not target only the performance of the material, but also its sustainability. And these are the main goals which our research relates on, trying to develop energy efficient recovery of materials, so so-called recycled materials, which we use as sustainable precursor for the production of novel materials and products. We address the term of materials criticality and try to substitute critical materials by using more sustainable substitutes and alternative materials, and trying to develop novel materials being capable of regeneration, being capable of reporting damage, and so on. So, and within this context, maybe I will just bring the term of circular economy, why this is important, and which concepts you might follow up in order to address this. This means that you would like to keep in the loop and the materials you use for the development of a product, for instance, and try to minimize as good as you can, because you cannot completely get rid of the residues and the contribution of primary resources. So typically, you would First, if you just imagine here on the top, you would have the primary raw materials which you will consider to produce your product. You will sell, you will have the use phase of your product. Then you will collect end-of-life products. And then you will try to see what to do with those, remanufacturing, reuse, or recycling, to get secondary raw materials to be then used for the production of new products. So the more secondary raw materials is used and the less primary raw materials, the more efficient will be this loop, and the more efficient you will be able to apply this circular economic concept. And these are the main targets which we are also following at Fraunhofer IWK. We try to minimize the use of primary raw materials. And obviously, this is not the main point to be addressed specifically, but also you should try to minimize residues and losses in the course of your production, for instance, right? And this should be considered mainly as important as the closing this material loop by considering secondary material. And one main consequence of this is that you have to fight against entropy. So you should try to minimize the entropy increase across these various added value chains or loops. And this is quite a challenge because you know that entropy is quite powerful, right? So, and I just brought you a very profound picture for that. This is a sort of situation which you would say high disorder, right? So high entropy. And this is a situation, would you say, at least lower entropy. So obviously, this should be the concept to follow up if you would like to address and fulfill these circular economy concepts. And I just brought you one example related to our research at IWKS, considering concepts and paths to reduce this entropy. So typically, the concept is very shortly summarized on the top. You have a high entropy state. You should input energy to get a low entropy state or a lower entropy state. And this is one use case for plastic waste streams, which are highly heterogeneous, and obviously they provide a high entropy state here, as you will see it here. And what you need is to put a lot of energy and know-how in order to get, for instance, compositionally pure and so on. Okay? And this is typically done with very complex procedures, and we develop, for instance, within a very large project which is called Waste for Future concepts to get a very effective sorting and separation of polymeric fractions from highly heterogeneous plastic waste streams. And we try to doing this in a knowledge-based and automatized way. So typically, we develop at our institute an evaluation model, which is machine learning assisted, and in a additional institute, another Fraunhofer Institute, there is a digital twin activity which is developed there in order to address various possible ways of separating and sorting, of reducing the entropy of these highly complex streams, and trying to evaluate what is the cost or energy costs and other costs if you start with a highly complex composition and you try to separate the valuable fractions by using various purposes such as mechanical, solvent-based solvolysis and pyrolysis assisted procedures. And we're trying to do this sensor-based and AI assisted in order to have a quite effective and not time-consuming way of recycling and circulating this type of waste streams. So this, however, a very classical way of trying to reduce the entropy state of a system and trying to get high purity fractions from your processes. So the idea and the questions would be, can we take advantage of the entropy to follow up our purposes? So we have seen, if you want to circulate materials, especially because you want to address waste as secondary raw material resources, you need to reduce the entropy. So the idea would be, can we take advantage of the entropy and trying to address the same purpose? And I just brought the concept of compositionally complex materials. This started around 20 years back when people began to develop the so-called high entropy alloys. So these are compositionally complex materials which have at least 5 components in their structure. And I think around 10 years later, this concept was applied also for ceramics. And you discuss about compositional complex ceramics or high entropy ceramics. And these are materials, ceramic materials, having more than 5 metallic cations, for instance, in their crystalline structure. So this is a single phase material. If you just think of rock salt oxides, this was the first example of a compositionally complex ceramic published in 2015. Instead of having only magnesium on the cationic sublattice, you will have at least 5 components there. But still one lattice, still one phase. And you see, meanwhile, within the last 8 years or so, a lot of dynamics evolved, emerged in this field, and many crystalline structures were developed with this concept of compositionally complex materials within the context of ceramic materials. And I just brought you a few. I mentioned that the talk is not very technical, but I still brought few examples from our research within this context of compositionally complex ceramics, where we try to develop rather simple synthetic approaches to generate these highly complex compositionally complex materials. This is a rather simple system from its crystalline structure because it's a spinel type oxide, but instead of having just magnetite, for instance, with iron cations in the sublattice, we put at least 4 other components and cations. And this is a very simple synthetic approach in which you take the nitrates and you grind this, you mechanically grind this with ammonium hydrogen carbonate. You will get a sort of reactive mechanical grinding with a sort of hydroxycarbonate, complex hydroxycarbonate as a product, which deals as a precursor for the resulting compositionally complex oxide. So if you take this precursor and you do a calcination at moderate, at high temperature, starting with 200 degrees C, you will see the formation of this spinel type oxide. Okay. And this is a concept which is called solvent efficient synthesis. This was published a few years back, I think 2015-16, within the context of the question, can we prepare, synthesize in a very simple way nanoscaled oxidic nanopowders? And this was shown for binary oxides to be very successful, and we could show that this concept applies also for these rather highly complex compositions on oxides. This is also a very nice example. This is a Bixby type oxide, also with complex composition, six metal cations in the sublattice. And I just want to emphasize here the precursor of this oxide, which is a hydroxycarbonate, which you get also in the same way. You take the nitrates, no solvent, you just take advantage of the hydrate crystal water, and you grind this together with ammonium carbonate. What you get out, it's a single phase compositionally complex hydroxycarbonate. This is quite interesting because you do not need any thermal treatment to force this 6 component to go into the same lattice. This is, for me, a good hint that this is an entropy-driven process, right? So, and then you see here on the left side, this 6-component hydroxycarbonate, which we use as a precursor for the Bixby type oxide, which was obtained just mechanically grinding the components at room temperature, right? And then you take this one and you expose this to calcination temperatures around 500 degrees C, and you convert this into a single-phase Bixby type oxide with complex composition, right? So this is just some examples which we showed within the context of generating, accessing composition complex oxide. This is one example of a non-oxidic composition complex ceramics using some precursors, because I promised to Ravi Kumar and Günther Motz that I will bring also some precursor-related results today. So this is a rather simple approach using polymeric precursors to generate ultra-high temperature ceramics, which we showed for binary ceramics, for zirconium carbide, for instance. And you can apply this concept, which is rather simple, for generating these compositionally complex UHTCs. Okay, you see, we generate a series of compositions with increased complexity, starting with ZRC and increasing the compositional complexity up to 6 components. So the question is now, because I brought you a few examples related to this concept and this synthetic strategy to generate these materials, how this correlates to our question of entropy and circular economy concept. And I just brought you at the end of my talk one use case which you might address to this, and this is what we're currently working on and addressing, to use, for instance, waste pickling solution as valuable precursors for preparing these compositionally complex oxides, which might be interesting material, for instance, for electrocatalysis or for some thermoelectric application. Okay? And I think at IIT Madras, I do not have to explain what is a pickling solution, because you are more experts in metallurgy than I am. But this generates a lot of waste, this pickling process, right? This surface treatment solution, because you need acidic solutions and you generate huge amounts of this spent pickling solution. You see for EU, 308,000 cubic meter of spent pickling solution. And typically, people put a lot of effort into recovering the acids from this pickling solution, but the solid content of this is getting landfilled. So, and this is a big waste, because you have large amounts of valuable metal oxides which are hidden there and which you might recover. And this is indeed some efforts to recover valuable oxides from this spent pickling solution, but the people really look for high purity materials. So taking a look how I can get high purity magnetite from this pickling solution, which you can use for whatever ferrite purposes. And our approach here would be how I can do this recovery process in a very simple, or the most simple way as possible, just not going for high purity materials, but just trying to get these compositionally complex materials out of it. And I will be finished in 1 minute with that. I'm sorry. So this is more or less what you would expect from steel pickling. This composition, you see you have some content of iron, chromium, and nickel. So you might put a lot of effort to get, for instance, high purity iron oxide from that. Or you might take a look, can we get compositions which involve all these metals, and I spare a lot of effort and costs related to this separation and purification. So you see, if you just take this modulated model spent pickling solution, you will end up with some bimodal phase compositions, but you can adjust this composition and you can adjust the thermal treatment in order to indeed end up with single phase compositionally complex oxide materials. And this might be interesting product for some prospective application. And with that, I'm just coming to a conclusion. I hope I could show you in this short time that typically if you follow up circular economy approaches, you should fight with a powerful enemy, which is the entropy. And I showed you probably and I hope convincingly, that this compositionally complex concept might help to use the entropy as a friend for addressing circular economy aspects, trying to develop materials with compositionally high complexity and high configurational entropy. And ideally, you can see this also in a broader scale, so not only using high entropy compositions or compositionally complex material, but also trying to develop material which are robust in their function and they can adapt a lot of impurities. So if you develop a material having a specific functionality, which in addition to that can support a lot of impurity, you have a very robust and strong material in hand, and you can pursue quite interesting application with that. So, and with that, I would like to thank again for the opportunity to be with you here and share with you these results, and thank you for your attention.
Thank you, Emmanuel, for this really nice presentation and letting us know what you are doing now. So the presentation is open for discussion now. Is there a question? There, over there.
Thank you very much for explaining nicely that we should go to the lowest entropy state. Just maybe one additional point. Do you consider that we should go for the lowest entropy state or lowest energy state? Say, although it may be similar. Right?
Yes, yes.
But I think entropy, what you shown actually when you were handling with too many compositions or too many materials, right? Or too many atoms to form a compound. That maybe entropy can be different, high, right? But it can form it can have a lowest energy state so that it's more stable. So maybe that may be desirable. So I don't know that's nearly same, but we need to think of that. Shall we go for the low energy state, or is the primary logic to go for low energy state or low entropy?
Yes, definitely. That's a good point. So this question was put within this narrow context of having highly complex composition in the stream and trying to address this concept. Should we always fight against the high entropy state, or we can take advantage of it? But definitely you should go for processes which provide you with the lowest energy consumption. This is definitely important, and you should consider this a bit holistically, a bit broader context than this one which I presented today here.
Yes.
Hello. Hello. I am asking that this high entropy oxide is stabilized at higher temperature itself?
That's depending on systems, but these are very interesting materials. So if you will take a look at the people reporting on those, there are different concepts which are followed. So one is low energy structures, because they are also robust with respect to some add-on and impurities, and they do not collapse, but they still are there. But also this additional and sometimes quite important contribution from the configurational entropy, because this adds also to a positive change in the Gibbs free energy, right? So if you have a significant amount contribution of the configurational entropy, you might think also that there is an entropic stabilization of your material, right? And this is especially strong at high temperature. Okay, what people doing, if you go to high temperature, you always can expect that these high compositions might be generated. However, at lower temperatures, you might have a demixing. And however, if you have this configurational entropy being indeed active, you will stabilize this. So this is a strong contribution to the stability of the material.
Okay, and instead of, say, for precursor, if we're using nitrate itself, instead of using nitrate, some other precursor if you use, is there any effect in the stability again? The changes in the stability of the system of entropy?
So if you use other precursors, so this is typically depending also on the compositions you target, but we could show, for instance, for carbides, that you can stabilize the same composition by using different synthetic approaches. So you can use a rather salt approach or a polymeric precursor approach. These compositions, if they have this high entropy stabilization, they come out. Yeah.
Emmanuel, very interesting talk. While this is very scientifically interesting, my question is, what is the technological potential of these class of entropy stabilized materials, particularly in the context of thermostructural applications? It's one thing to stabilize it, but to what extent and to what, how long can you stabilize it? For example, if you keep the same material for an extended duration of time, do you still think that the material will be remain stable?
So this is probably within the context of this carbadic high temperature stable materials, which is quite interesting question and aspect. So my personal opinion is, and we have some hints and results related to that, is that if you just consider the thermal exposure, temperature exposure, these materials are predestined for this application. What you should consider is the oxidation and corrosion at high temperature. And if you address this, then you should carefully choose your compositions, not only related to the materials you would like to synthesize as thermostructural materials, but also with respect to which scale, composition the scale will have. Because in most of the case, this compositionally complex single-phase material provides you with highly heterogeneous composition in the scale, and this is rather detrimental then. So this is an additional challenge then to design those materials.
Can I ask one more question? Just one more short question. How easy it is to keep a single phase when you make it in large quantities and when you want to make a product, for example?
So I cannot answer this question. So scaling up, it's not yet done at our place. So we definitely target for this, especially if you target these use cases with these huge amounts of precursor, secondary raw materials. But definitely this is an important aspect to be considered, yeah.
So thank you very much for this nice discussion, and I suggest that we postpone or discuss further questions during the next days. Thank you once again, Emmanuel, for this nice presentation.
Thank you, sir. I now request Dr. Michaela to present the memento to Dr. Emmanuel.
So with that, we move on to the second presentation of this session, and this will be given by Sujit Ravindran. So I would request him to come to the stage. Thank you. So he's an associate professor at the Department of Mechanical Engineering in Hyderabad. So, and he will talk about the topic silicon oxides, oxycarbides as anodes for lithium-ion battery.
Okay, good evening everyone, and I'm a little nervous because after 9 years I am presenting before my guide, so something's technical. Okay, so today I am going to discuss something on, close it. Okay, so today I am going to discuss something on lithium-ion batteries. Basically, how PDCs, polymer-derived ceramics, can be used for as anode materials in lithium-ion batteries. It's a very basic level talk. It's not going to be a very deep scientific talk or anything like that. This work is mainly done by my student Gangadhar. He is now in Ola Electrics as a battery scientist, and And part of the work we did at Clemson University with Professor Bodia. And Dilip is the postdoc of Professor Bodia. Okay, one more thing, and this work was funded by HBL. It's actually a battery manufacturing industry in Hyderabad. So let us go into the talk. So basically, if you see here, it's a schematic of lithium-ion batteries, and lithium-ion battery is basically an electrochemical cell. It has got a cathode and an anode separated by an electrolyte. And during charging, what happens is that the lithium ions from the lithium metal oxide will move towards the anode through the electrolyte. And during discharging, what happens is that the lithium ion will go back to the metal oxide. So that is how it works. But if you see here, the anode material is typically in lithium-ion batteries, it is graphite. Graphite is the material which is commonly used. But what we have proposed or what we have done is actually replacing this graphite with silicon oxycarbide. And to that we have added graphene also to improve the properties. I will discuss about that. So why silicon oxycarbides is the question, and we will try to answer it. And to start with, graphite is the typical material for anodes. And if you see the graphite, graphite is a widely available material, it's very common material. And the lithium actually goes, during charging what happens is that lithium goes and sits between the layers of the graphite. It's known as intercalation mechanism. So it intercalates between the layers of the graphite. And if you see here, this blue colored thing is nothing but the lithium. My hands are shaking, that's why. So the blue colored thing is the lithium, and surrounded by actually the carbon. Okay, so 6 carbon. So lithium LiC6 configuration. So that will lead to a storage capacity of 372 milliampere hour per gram. This is actually the theoretical capacity for graphite, but it looks good. It can be used for electric vehicles and is already in use also. But the problem is that it's not a problem. It's the constraint is relatively low specific capacity, 372 milliampere hour per gram. You can replace it with some other materials. We can get much better capacities. One solution is replace graphite with silicon, and because silicon is in the same table, same group as in the periodic table, and it has got a theoretical capacity of 4,200 milliampere hour per gram. And if you see the number wise 372, 4,200, it is almost 10 times or more than that of graphite. But the alloying the mechanism involved is different here. It is not actually an intercalation mechanism, it's an alloying mechanism. So the lithium actually dissolves in the silicon, and you can see that Li22Si5, which means that one silicon will have approximately 4.4 lithium ions it can take. So it looks very good, and it means that you can simply replace graphite by silicon, but it doesn't work. It doesn't work because of the high volumetric expansion, because of this intercalation mechanism. So there is a huge volumetric expansion, and the expansion is approximately of the order of 400%, 300 to 400%. And what will happen is that because of that, there will be crumbling of the electrodes may happen, and there may be lack of connectivity between the particles may happen, and property degradation will happen. You can see one galvanostatic charge discharge study. You can see that the first cycle, the capacity is around 3,000, and during charging, and it has come down to around 1,000, and it gradually shifts towards, the entire thing is shifting towards the left, which actually means that there is a lot of degradation or structural instability is there for these materials. Okay, so the solutions, there are many solutions. The one is to reduce the size of the silicon, and that is what is being demonstrated here. So if you have a film like silicon, after cycling it will get crumbled, or you can have particles of micron size particles, they also may get crumbled. But if you grow it like a one-dimensional nanowires of silicon, this is actually the silicon grown in steel substrate, and you can get a very good connectivity. At the same time, these will not crumble. Okay, why it is not crumbling? It is because of some mechanics reasons. There should be something like a critical size. So if the critical size, particle size is something less than 150 nanometer, if you can make it, you can actually produce silicon batteries which are very stable. But the problem is making it developing this system into an industry level, because you have to grow it like CVD based process or something like that. It's not an economically viable process. Okay, so that is a major issue. But otherwise, you see here the reversible storage capacity is 4,200 milliampere hour per gram, and with a Coulombic efficiency of approximately 73%, which is actually quite good for silicon, because there is a lot of irreversible reactions associated with silicon. What is this Coulombic efficiency? I hope all of you know that. Coulombic efficiency is the discharge to charge. So if you have 100% Coulombic efficiency, it means that 4,200 during charging, discharging also 4,200. That's actually means. So for 73% is quite good actually for lithium, but this is a very expensive process. Professor Q's group from Stanford actually has developed commercially made silicon-based batteries is available, but its only thing is that it is expensive and it is may not be viable for at least for Indian conditions. Other strategies, you can embed this silicon so that the silicon is embedded in some amorphous network of even silicon oxycarbide. So you can embed this silicon in a silicon oxycarbide matrix. That itself can actually act as one way to prevent the crumbling of the silicon. Or you can use amorphous silicon, because when you have amorphous structures, the free volume of this material system is higher. So the amorphous structures can accommodate more volumetric strains compared to that of crystalline structures. So amorphous is another option. So you can actually increase the critical particle size. So you can see that from around 150 to 900 nanometer you can go, but the problem is that your capacity comes down. So when you have a crystalline system to an amorphous system, the amorphous system will give you a lower capacity. But you can also go with mesoporous system or porosity in the silicon, because the porosity again acts as like a shock absorbing can help in accommodating the volumetric strains. Or you can have silicon oxides, or finally you can have something like silicon oxycarbide. So something that is what we have actually tried out. It's not the new thing, it has been there since I think 2012. Professor Rishiraj groups and so on, they actually worked on silicon oxycarbides as anode materials in the form of films and so on. They have demonstrated it way back in 2012. So why silicon oxycarbides? There are a lot of reasons. One is that its specific storage capacity is quite good, twice that of graphite. But there is a problem which I will tell you, which I will discuss with you later. It is twice that of graphite, but not necessarily always you will get twice the specific capacity of graphite. It is one big problem with polymer derived ceramics. Repeatability is something which is, because it's a very heterogeneous structure, I can synthesize one polymer with some specific capacity. Professor Ionescu can synthesize another polymer through another polymer with another specific capacity. So it's very wide range you can see in the literature for these specific capacities. And another interesting nature of these polymer derived ceramics is its amorphous nature. It depends upon the pyrolysis temperature. Several studies have shown that if you pyrolyze it to very high temperatures and make it phase separate and crystallize, its capacity comes down, because silicon carbide formation, for example, in silicon oxycarbide, it phase separate and forms silicon dioxide and silicon carbide, and silicon carbide is an inactive phase, so it is not good. The other way, the third reason is free carbon. Free carbon is also very complicated. Sometimes it will result in disordered or turbostatic free carbon. Sometimes it results in ordered. So it's again another level of heterogeneity in the system. But free carbon will help. It will also help in increasing the electrical conductivity to a certain extent, presence of free carbon. And then the microporosity. PDCs are always porous because it's produced by burning polymer. So the structure is always porous, but you can control the level of porosity by doing maybe by etching or doing some alternative process, and the flexibility is always there. As I mentioned, different polymers, if you use polymeric precursors you will end up with different. But there are a lot of limitations as well. For example, the Coulombic efficiency, if you see, the initial Coulombic efficiency is 60%. This is something which is I took a very high, reasonably higher value. If typically it can come down very less. It can come down to below 30 or sometimes 20% also, the initial Coulombic efficiency, the first cycle. And often we do not report this first cycle Coulombic efficiency. We start from the next cycle onwards where the Coulombic efficiency gets more or less stabilized. So that is one big problem or challenge with silicon oxycarbates. Lot of reversibility may be there in the initial reactions. So that has to be overcome by designing the polymeric precursor perhaps. And the electrical conductivity is again very less. You have to add something to improve the electrical conductivity. This third point is not very clearly studied. The interfaces which is there, the interface between the electrolyte as well as the current collector. Okay, so usually the current collector, the commonly used current collector is copper. But what we did is we tried to replicate what is there in the literature many times, but we were unable to produce. We did it in IISc Bangalore, we went many places, but we are unable to reproduce the results which is there in the literature. And we think that it is basically because of the interface problem. It is not properly adhering to the ceramic is not properly adhering to the copper, so there is no electrical connectivity between the ceramic and the collector. And the fourth point is my diverse microstructure. So it's underlying because its mechanisms are very complex. So why it is complex? It is because you see that SiOC is a heterogeneous system. It has got 3 possible sites, so 3 possible mechanisms or more than 3 possible mechanisms. One is that interstitial spaces in free carbon. The free carbon itself can act as a storage media. In addition to the silicon oxycarbide. So there are certain systems where silicon is the dominant system. There are other systems, same PDCs. There are other PDCs where the free carbon or the carbon is the dominant system for storing hydrogen. So that is another confusion which creates, especially in this PDC literature. And then you have the microporosity. The pore sites will act as can act as increase the surface area, specific surface area, and therefore this can also contribute to the lithium active sites. Okay, so that way that is also another contribution. So which one is more dominant is something which is not clearly understood. I think it has to be further studies are required to understand why which mechanism is dominant and why one mechanism dominates over the other. And we have done some studies, and I think, you can see here, there are a lot of curves. You do not have to bother too much. So there are, you have to see only the blue curve and the green curve. And the blue curve corresponds to silicon oxycarbide 1, which is actually a carbon-rich ceramic. And SiOC2 is actually a silicon-rich ceramic. And you can see that the silicon-rich ceramic is having higher discharge capacity when compared to a carbon-rich ceramic. And this is quite logical because silicon is having a much higher storage capacity than that of the carbon. So it may be like that. But there are literature which shows that just the opposite of this, the carbon is contributing more to the hydrogen, more to the lithium storage compared to that of the silicon. Okay, so this is one point. And why we think that silicon oxycarbide 1, which is the carbon-rich system, is having lower capacity? It may be because of this irreversible SiOC3 formation, which we do not find in the other system. Maybe that could be the reason why SiOC2 is performing better when compared to SiOC1. And the storage mechanisms people have studied by using first principle studies, using density functional theory and so on. I don't want to discuss too much here, but one point here is that initially what happens is that during the lithium storage, initially the silicon oxide bonds are broken, and then the lithium reacts with oxygen and form lithium oxides, La2O. And further what happens is that these lithium silicides and lithium oxides further are formed. And please note that these are sometimes irreversible reactions. So it will actually bring down the Coulombic efficiency. But there is an advantage. There is some advantage here. The advantage is that this will act as something like a cushioning thing, which gives further stability for the system. So the stability increases at the cost of maybe the the capacity, storage capacity. Very interesting thing what they found is actually the carbon do not attract lithium. So this is something which is found in the density functional first principle study. I don't want to confuse further because there are again certain other first principle studies which says a slightly different thing, but maybe because of the configuration of the initial polymer, initial ceramic they took, they resulted in different results. Okay. And where there are ways to enhance the electrical conductivity, a lot of studies have been done. One is by adding graphene. So what we have done is that added graphene and we can increase the conductivity significantly. And these TEM images were taken from Germany, actually from Karlsruhe Institute. They actually saw something from German. Okay, so what we can see here is that this type of diagrams already has been shown before in the morning session also. So, so you can see that what we found is a graphene dominated system is found to have a better performance when compared to that of other systems. So, so 75% graphene and 25% silicon oxycarbide seem to perform better compared to that of the other. We are not saying that this is the optimum thing, but this is something which we observed. And also it seems to be more structurally stable also compared to that of the other systems. Okay, so that is something which we have observed. And the interface. This is something which I wanted to tell because we took the interface. This is the ceramic and you have the copper here. And the coating looks good, but somehow we were not getting the results from this system. And we measured the contact angle also. The contact angle was found to be around 70 degrees with copper as the collector. We did the same with bucky paper also. Okay, why we gone to bucky paper is to improve the wettability. So we did contact angle measurements, and the mean contact angle comes to around 24 degrees, which is more hydrophilic. It's more wetting compared to that of. It's quite natural also because bucky paper and silicon oxycarbide is basically a carbonaceous system. So maybe improving the wettability. I don't have the corresponding SEM image because I don't have the image of with the same scale, so I did not put it. But you can see that clearly bucky paper is having a better wettability when compared to that of the copper. So one option is to replace copper with bucky paper, especially in PDC systems, to improve the performance. But that may also be a challenge because it's not that economical, because you have bucky paper is extremely expensive material, and but it can be considered for something like flexible batteries. So in future, if someone interested in flexible batteries and so on, because graphene has got this flexibility, you can think of using this for flexible batteries. So there are several other strategies, something like creating a microporous structure. That's what I was saying. You can etch it with fluoric acid. But the problem is that there is a point here. When you etch it with fluoric acid, you can increase the porosity, but at the same time you will lose the site. Silicon oxides gets dissolved, and you may lose the site, the active sites for lithium storage. So this is one thing which may happen because of etching. So you may have to go with some other alternative solutions, making morphological changes, make it spherical instead of film-like. There are studies which shows that if you make it spherical, it shows a better performance when compared to film-like structures. Modify the synthesis route. Pre-lithiation is something which can be done, which has been tried out also. Pre-lithiation will increase the initial Coulombic efficiency because it's already lithiated and the secondary reactions are done. So, so you will get a better Coulombic efficiency by pre-lithiation. Okay, so I am not going to discuss further in this. We have written a review paper with Professor Bodia, and it may come in another 2-3 months, and those who are interested can read about these. And other electrochemical applications of silicon oxycarbides, there are several other electrochemical, 5 minutes. One is, as I said, we can improve the electrochemical performance of the silicon itself. You can improve the structural stability of the silicon by encapsulating silicon in silicon oxycarbides. So silicon oxycarbides is not actually doing the major electrochemical, is not contributing the major electrochemical performance, but the silicon is contributing, but the silicon crumbling of the silicon can be prevented, can be avoided. And lithium tin batteries, again, tin has the same problem like silicon. Its volume expansion is very high. So you can also encapsulate tin with silicon oxycarbates or any other polymer-derived ceramics, amorphous structures, and improve the performance of lithium tin batteries. Sodium-ion batteries, supercapacitors. So there are many options for these electrochemical applications of these PDCs. Okay, so finally, this may be sometimes controversial, or these are my perspectives, may not be everyone agreeing with me, but my thing is, first of all, when I tried to work with lithium-ion batteries, especially for an industry, it was very difficult to zero down to a material, because there is a wide range in the literature from 200 milliampere hour per gram to 1300 milliampere hour per gram, and there is no consistent result. So that is one major issue with PDCs. With Sir, we have written on review paper, International Materials Reviews. There also we found, even in structural properties, when we tried to see on the whole, it is very difficult to find PDCs having repeatable properties, or different people come up with different reasons for different properties and so on. So this is one thing which is very confusing with PDC literature. And the second thing is that interaction of silicon and based anodes with different parts of the batteries is well studied. But interaction with silicon oxycarbates or PDCs with other systems like electrolytes, collectors, brine tests, what is the effect, is not very well explored. So this is another point which can be explored in the future. Mechanical stability, other than, I have seen only one paper which published in Nature Communications from Gurpreet Singh's Sir's lab. So where they have studied some flexibility studies of a graphene-based system. Otherwise, mechanical studies, as a mechanical engineers, we have a lot of scope of doing it, because the structural stability is not very well understood. I will conclude in another 2 slides. So the last point, okay, this is the last point, is mainly, as INSQ sir was saying, what is the sustainability of these PDCs? I have serious doubt about the sustainability, because when I was a student here, Srinivasan also maybe knowing it, when we tried to pyrolyze these polymers, we were not allowed to pyrolyze during the working hours. Why? Because a lot of fumes comes out. So we have to do this pyrolysis only in the evenings or in the night. So if you see here, we are talking about batteries and so on, talking about green energy and so on, but we are taking a polymer which is basically pyrolyzing it, and in the process we are actually evolving a lot of carbon dioxide and so on, or other carbonaceous gases. So are they really green? So that's why I put it gray, and today is Holi, so maybe we can consider this as a gray, because in hydrogen storage we have something like hydrogen production, we have different colored hydrogen, so gray hydrogen, green hydrogen, blue hydrogen, turquoise and so on. So maybe green gray lithium-ion batteries. So with this, so I believe there is a lot of distance to travel before it can be finally be implemented at least in an industrial scale. So thank you. Happy holiday.
Thank you very much, Suji, for this nice presentation. So, questions? Oh, I see already one.
Thank you, very nice talk. Could you explain the morphology of your anode material? Are these particles like traditional cathode anode active material? Or is it a continuous layer? For me, it was not clear.
Yeah, it is actually particles, and then we actually dispersed it on the surface of the collector.
And by doing what is the size of the particles? Can you control it?
It's around 200 nanometer particles.
Okay, very fine.
We did ball milling and reduced the particle size.
Okay. Yeah, thank you.
Over there.
Yes, thank you. Very interesting talk. So I just have a question about the microporosity. So you showed the difference between the carbo-rich and silico-rich, but you didn't say anything about microporosity. I expect also microporosity is different.
Yeah, correct.
Is this one as one thing? And second thing, also you said what is common, we will do it using HF for etching and induce microporosity. But also we have some work in the past by controlling the polysiloxane.
Yeah,
cursor.
You can change the polymer chemistry and change the porosity levels.
Have you tried this?
That is another option, but we have not tried it. Yeah, you cannot make an one-to-one comparison in these systems because one may be having a little bit more porous, because the factors are too many here. So the porosity also plays a very important. True, sir.
I have one question. Yeah. You are mixing graphene with silicon oxycarbide, right?
Yeah.
SiOC. You are putting 75% of graphene. Right?
It's not mixing after the powder is produced.
So it is not homogeneous.
It is homogeneous. So we assume it is homogeneous. So what we do is PDC, we make it, we make the ceramic and then add the graphene particles and then we do the ball milling and do the mixing.
Okay.
Not in the polymeric stage.
Okay,
Finally.
okay. After making the powders,
Yeah,
you are
after
mixing
making
it. Okay. And you are milling in dry milling or liquid milling?
Dry.
Dry milling you are
Yeah,
doing.
yeah.
So graphene is not
not
getting
oxidizing
affected.
or something?
Yes, yes.
We have not seen, we have not studied, maybe.
Okay, thank you.
Hello, thanks for the presentation. I have a small doubt. So would it be possible to use a copper modified SiOC to make a better interface with the copper collector?
I
Would
think
it helpful?
it's already too much complicated silicon oxycarbide. So further adding another element and making it further complicated, I don't.
Because you're telling it is not, interface is the main problem you're telling with the copper.
I think if you add copper, the problem is that the weight of that thing will also contribute, and the specific capacity is going to come down of the system. So I don't think it is a good solution.
Okay.
Maybe you can try.
Thank you. So I would like to thank you once again for your very nice presentation.
Thank you very much, sir. I once again request Dr. Michaela to present the memento to Dr. Sujit. I now request Dr. Günther Motz to present the memento to Dr. Michaela. With this, we have successfully concluded our day one interviewing lectures and discussions. I now request Dr. Ravi Kumar to say a few words, and then I talk about what's going to be there further in the evening.
If you want your money back, please give your boarding passes to us. If you want your airfare to be reimbursed and so on, so please do not forget to hand over the boarding passes to the front registration desk. There's an orange colored tray at the registration desk outside this hall. Just please drop your boarding pass there so that we can process your airfare. I think those who have come from Lufthansa, possibly you have an electronic boarding pass. I think you can send forward your electronic boarding pass to help desk so that we can initiate your reimbursement. If you have not given your bank details, then we will have to send the money back to IGSTC. So please provide your bank details as well. This is applicable for both German guests as well as the Indian guests who are part of the IGSTC. So we have a cultural program at 6:30 here. So 6:30 is the instrumental music program. It's in the same place here. So we still have like 1 hour, a little more than 1 hour. So there are 1 or 2 maybe transport vehicles which can take you to the guest house. If you want, you can use the transport vehicle or you can walk. But please make sure that you are back here by 6:15 or 6:20. So the artists will be here, I think, anytime now, and they'll get ready. We need to just arrange the stage here for the artists to be ready for the concert. So please do come back here by 6:15. Last but not the least, today is Holi. Happy Holi. We would have loved to smear you with colors here, but unfortunately, if I do that, I will be subjected to administrative action by the institute. So I cannot do that. I cannot destroy this place. So what we can do is, we can destroy your clothes. So while you are going out, we have the possibility to smear colors on you. If you are wearing a very formal dress and if you want your formal dress to be protected, then you can politely say, please don't apply colors on me. But if you think that you are a little bit adventurous, please allow the girls standing outside to apply colors on you. However, the girls, I have told them not to apply, with restricted access. So at the most, they may apply on your forehead and cheeks. So it should not be too much of a problem. But if you have any issues with allergy with respect to colors and so on, please tell them not to apply. Nothing will be forced on you. But if you are okay to be smeared with colors while you are going out, please be prepared for the colors to be applied on you. That's Holi. So happy Holi. And of course, after the colors are applied on you, we will be happy to take a photograph with colors so that we have some kind of an evidence that you were subjected to Holi celebrations. I think that's it from my side. So please go out and then come back, have shower if you want to, and leave your laptop, come with a relaxed clothing back to the same place. And again, from here, we will, after the concert is for about 1 hour. So it is from 6:30 to 7:30. At 7:30, we will leave from here to the alumni club, research, which is located in the research park. And the dinner will be there in the club. But we will start from here. It is walkable, but I think in order to save time, we have arranged some transport again. So immediately after the concert, which ends at 7:30, we will immediately go from here directly. So if you want to change, please change and come back. So I think that is from our side. If you have any questions, please let me know. But please hand over the boarding passes outside at the registration desk. You can also do it tomorrow, but please do it as soon as possible. And do not forget to bring your dinner coupons, because this will be in a restaurant, and also I think if alcohol is served, then you cannot use the alcohol services there. So please bring your food coupons as well as your coupons for the drinks. You are not obliged to drink alcohol. You can be drinking juices and so on. But if you want to drink, you need these coupons there. So please bring them with you when you come back. Any questions? Yeah.
Easy.
How difficult? We will not apply on your shirts and pants. It will be applied on your. It's only a powder that will be applied on your face. If you do not want, you can always say no to the girls standing outside. But you can wash it easily. You are not obliged to. You don't have to use ethyl alcohol to remove it. If people apply, see, people agree, because we do not want to force, and there may be people who may not like it. So please obtain consent before you do whatever you want. Yeah, that is fine. Thank you. Please come back by 6:15 here to the same place. Thank you.
Good evening. Welcome back to the first day of workshop. Now, here we will have our cultural event under the workshop titled Recent Advances in Precursor Derived Ceramics, Innovation and Translational Research, PDC. So, I would like to introduce to the artists of the today. So, starting with Srimati P. Sujana, who will be playing the veena. Then next is Kumari V. Deepika, who will be playing the violin. Third one is Shri S. Vishwas, who is on mandolin. And next is Shri R. Ananthakrishnan, who is playing mridangam. And the last but not least is the Shri S. Shunil Kumar, who is playing kanjira. Over to you, Shri Vidya.
Hello, good evening. I would like to take this opportunity to introduce the various types of compositions that the artist will be presenting today. First, they would be starting with a varnam. A varnam is a type of composition in the Carnatic music system that encapsulates the key features of a raga, which is the melodic framework, and considered as a foundational element in the learning path. A varnam is traditionally performed as an opening item by musicians in Carnatic music concerts. Today they will be presenting Hamsadhvani Varnam, Jalajakshi. Next will be a kriti, which is a song. They are a delicate blend of text, melody, and rhythm, and are the most popular items of a South Indian concert. The song that they will be presenting is Shobhillu Saptaswara, composed by Sri Tyagaraja, who is one of the Trinity, also known as one of the jewel of Carnatic music from the 18th century. In this composition, the composer describes the greatness of music. He tells his mind to worship the radiant Saptaswara divinities, swara referring to the musical note. Just like how in the European music you have do, re, mi, fa, sol, la, si, we have sa, ri, ga, ma, pa, da, ni. So presenting Shobhillu Saptaswara in Jagan Mohini set to a rhythm of 8 beats per cycle, the Adi Talam. Sorry, my mistake. It's a cycle of 6 beats per cycle, 6 beats per cycle, so it's Rupakatalam. Sorry. Next, it's a very interesting and beautiful composition that they'll be presenting. Ananda Amrita Karshini, Ragam Amrita Varshini. The raga is supposed to get rain. It is composed by Sri Muthuswami Dikshitar, who is also one of the Trinity of Carnatic music. Quickly sharing the beautiful story about this composition. Sri Dikshitar began to sing in praise of the Lord in a unique style by singing this song. He caused thunderous clouds to gather over the sky and rain profusely when there were no rains in village Ettayapuram in Tirunelveli district for 1 year. And the people of that village yearned for water. When he sang the line, Varshaya, 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 it started raining heavily, flooding the village. Presenting Anandamrita Karshini, Ragam Amrita Varshini, composed by Muthuswami Dikshitar, set to Aditalam, 8 beats per cycle. Next will be the main piece of the concert, a composition of Saint Tyagaraja, Samaja Varagamana in Ragam Hindolam, one of the most popular composition in Carnatic music. As you're also seeing, the artists on the melodic instruments are taking turns and coming on spot with some creative improvisations. You will get to see more of that in this composition, as well as followed by the Tani Avartanam, where the percussionists will exchange various complex rhythmic patterns culminating in a grand finale. This is usually played after the main composition of the concert, presenting Samaja Varagamana in Ragam Hindolam. We have now come to the end of the program. The artists would like to end their performance by playing the German and Indian anthem, requesting you all to rise for the national anthem. Thank you so much.
That was an amazing performance. I know that we are slightly delayed for dinner, but I should thank the artists. They are well-known artists. And I think on behalf of the organizing committee, I thank all of you for accepting our request to perform. On Veena, it was Srimati P. Sujana. Sujana is the wife of one of our faculty members. And on violin, it was Deepika, Kumari Deepika. And on mandolin, it was Sri Vishwas. On mridangam, it was Ananta Krishnan. And Sunil Kumar on Kanjira. And all of them are very well-known artists, and yeah, thanks to them. It was a pleasure hearing you. Thank you.
Now I request Professor Ravi Kumar to give a memento to our artist. First, I'll ask Professor Ravi Kumar to give memento to Srimati P. Sujana. Next, I request Professor Ravi Kumar to give memento to Kumari V. Deepika. Next, I request Professor Ravi Kumar to give memento to Shri H. Vishwas. Next, I request Professor Ravi Kumar to give memento to Shri R. Ananta Krishnan. At last, I request Professor Ravi Kumar to give memento to Shri S. Sunil Kumar.
We can head for lunch. Sorry, dinner. So we have the transport outside waiting for you. So I think one of yeah. So please head for dinner. Thank you so much. Yeah, thank you.